Ladies and gentlemen, very good morning and welcome to this plenary session entitled Contribution of Synchronous Compensator to the Stability of Invert-Based Generation. Let me take this opportunity to thank and congratulate all the organizers for their excellent work in putting together this conference. This session will focus on a topic that is currently on great relevance in Spain. It is likely that even those of you who do not reside in this country have heard about the blackout that occurred in past April. I find it particularly striking to witness discussion on the role of the inertia in power generation, not only in academic settings, but also in restaurants, on social media, and even in mainstream newspaper. It's my pleasure to introduce Dr. Luis Rouco Rodriguez, one of the most distinguished experts in power system. I am confident that the presentation will greatly enhance our understanding of this topic. Dr. Rouco earned both his master and PhD in electrical engineering from the Polytechnical University of Madrid. He currently serves as full professor of electrical engineering at Universidad Pontificia de Comillas, where he was also the director of the Department of Electrical Engineering from 1999 to 2005. For many years, he has led the joint Power System Operation course developed by Universidad Pontificia de Comillas and Red Eléctrica de España, the Spanish TSO. This course is considered a key training program for industry professionals. In the classroom, Professor Rouco teaches undergraduate courses in electrical machines and power system protection alongside graduate level instruction in electrical power system. His academic work is closely tied to the Instituto de Investigación Tecnológica, the IIT, where he carried out pioneering research on power system topics. His area of expertise include modeling, simulation, control, and system projects, collaborating with Spanish government bodies, major utilities, engineering firms, and even international organizations. Dr. Rouco has published more than 200 papers in leading international journals and conferences. Since 2029, Stanford University has recognized him among the top 2% of the world's most cited scientists. He is a senior member of the ICREPQ and a distinguished member of SIGRE. He also holds several leadership roles as president of the Electrical Energy System and the member executive committee of the SIGRE Spain and the working group devoted to rotating machines, editor for the ICREPQ Transaction on Power System, and chairman of several important conferences as the ICREPQ Power Tech. Dr. Rouco has also served as a visitor research at Ontario Hydro in Toronto, the MIT in Cambridge, and ABB in Vasteras. Professor Rouco, the floor is yours. Thank you very much.
Thank you very much for your very kind introduction. It's a great pleasure to be here 1 year more, trying to bring a hot topic on power system analysis, stability, and control. Today we will speak about the role of synchronous compensators in a power system driven by inverters-based generation. Okay, let's have a look on the agenda today. I will make an introduction, and then I will separate my contribution into two main parts. The first part is related of the contribution of synchronous compensator to the stability of grid feeding converters. Probably you have heard about the new technology of grid forming converters. Hopefully next year we will bring some results that we have already obtained in their interaction between synchronous compensators and grid forming. But today we will speak about the role and the contribution of synchronous compensators to the stability of grid feeding converters. But also we will speak about the contribution of synchronous compensators to the damping of electromechanical oscillations. You may have heard that one of the events that might trigger the blackout of the Iberia Peninsula on April 28th was the occurrence of inter-area oscillations within the continental European system. And then we will provide some conclusions. Okay, let's have a review on what is a synchronous compensator. Well, a synchronous compensator is a synchronous machine that only supplies and consumes reactive power. There is no active power exchange with the grid except of the losses. Well, they are not driven by a prime mover, and except that they are driven by an auxiliary motor during the startup process. Well, they were used in the past to provide continuous reactive power, voltage control, continuous capability. But they were surpassed by power electronic devices like static bar compensators because of the lower maintenance cost. You know, a rotating machine require more, the maintenance costs are higher than in an electronic device. Okay, there are in the market, I can bring two solutions. There is no commercial interest from my side and this. Here there are two commercial solutions available. One is ABB solution, and the other one is delivered by the Spanish manufacturer Ingeteam. The main difference between the two solutions is that the ABB solution has a separate flywheel. So as you can see here in the ABB solution, we have the electrical machine, the flywheel, and the pony motor, the auxiliary motor. However, the inverse solution does not require a flywheel. The mechanical design of the rotor of the synchronous machine also provides the inertia that in the case of the ABB solution is provided by the flywheel. Okay, let's talk about application examples. There are many examples of application of synchronous converters today worldwide. Of course, I must highlight what is happening in Spain. And as you can see, there is a big program, deployment program of synchronous compensators in Spain, mainly in the island systems. In the Balearic Islands, which are connected, as it was pointed out yesterday by Professor Antonio Gomez, is connected to mainland Spain through an HVDC link. In this system, in the Balearic system, synchronous compensators are mainly needed to provide the short circuit capacity that the LCC HVDC link needs. In addition, in the Canary Islands, there are a few projects, one in Tenerife, one in Gran Canaria, in the big islands, to add a synchronous compensator, and also in the Fuerteventura-Lanzarote system, which is two islands in the province of Gran Canaria that are linked by an AC link. There is another project. These projects has already been assigned to, I can say, but because it's public, to ABB. Of course, there are other solutions that there are other examples that are linked to to promoters that want to increase the short circuit capacity related to the grid access. As you can see, well, it's remarkable the example of Italy, where Tesla is deploying 16 synchronous compensators throughout the Italian system. There are many examples in Ireland, UK, US. Well, the case of the US is related to a big offshore wind farm in Massachusetts, Brazil, Australia, etc. Okay, which is the main motivation for the deployment of synchronous compensators? The transformation of the power system from a synchronous machine-based system to a system based on inverter-based generation. And the main differences between those systems are the inertia and the short circuit capacity. Synchronous generators provide inertia. Here I'm showing you the inertia that was provided by a nuclear station on the event of the July 24, 2021 in Spain, in which Spain became disconnected from the continental European system. And as you can see in the left figure, the power, the synchronous generator of a big nuclear station that was supplying in a steady state 1,092 megawatts, supply almost 80, 90 megawatts in the case of the frequency event. And also you can have on the right examples on the short circuit supply by this nuclear station. Okay, synchronous compensator could provide both services, inertia, and reactive power capability. Well, let's connect the synchronous compensators with inverter-based generation. The short circuit capacity of the grid determines the stability of the inverter-based generation. Manufacturers design the controls as assuming an impedance of the grid. So if the impedance of the grid is higher than the design assumed by the converters manufacturers, they might run into problem. So one approach to increase the short circuit capacity is to add a synchronous compensator. And that will be the topic of one of the topics of my presentation. Okay, here we have a very simple example on how to design and how to size a synchronous compensator if one needs to add to increase the short circuit capacity. Okay, let's go to discuss the problem of grid, the stability of grid feeding converters. I was saying at the beginning of my presentation that today we are not speaking about grid forming. Next year, hopefully, we will speak about grid forming. Okay, this is the type 3 wind generator, the electric circuit, the basic controls. I'm not going into the detail. I will go into the results. These are the control schemes of the type 3, the double-fed induction generator. We have controls on the rotor side and on the stator side. And also we have a very relevant component, which is the PLL. that provides the reference for the control, the voltage reference for the controls. Okay, what happens with the stability of this system? Well, the stability is affected by the grid impedance. So what we can see is that there are one mode that as the impedance increases, the mode becomes unstable, which is the one that is highlighted. So the cross is the starting point, and when I'm increasing the impedance, we are moving to the circles. Okay, and what happens if we incorporate a synchronous compensator? Well, we can do a very simple calculation, as I did before, to say, okay, the synchronous compensator reduces the impedance. But what happens, what kind of interactions do we have between the dynamics of the type 3 wind generator and the synchronous compensator? What we can see is that it's quite noble, the behavior, the contribution of the synchronous compensator is to increase the stability. As we increase the impedance, if we move, in the pink color, what we see is that the unstable mode related to the PLL is not, becomes, there is no issue with it. So the synchronous compensator is able to do the job with any adverse interaction with the controllers of the type 3. What is most important is that if we consider the other type of wind generator, type 4, which is mostly used for offshore generation, we have almost the same type of phenomena. The mode related to the PLL becomes unstable as the grid impedance increases. And once we install the synchronous compensator, we reduce the equivalent impedance of the grid because of the action of the synchronous compensator, and we have a higher stability margin. So what are the messages? The main message of this work is that with detailed models, the behavior of the system is very close to the simplified models. And the synchronous compensator is able to do the job and to increase the stability of the wind generators, as affected mainly by the control of the PLL. Okay, one interesting recall is that we have found, we have just approved a paper in the ICREPQ transactions that we have shown that in addition to the rating of the generator, it's important what is doing the synchronous compensator. If it's injecting or is absorbing reactive power. What we have seen is that it affects the voltage and the situation in which the synchronous compensator is consuming reactive power, well, the stability margin decreases. Okay, this is one of the topics that I wanted to share with you today. And the other topic is electromechanical oscillations. As I was saying, that one of the events that were around during the minutes before the blackout of the Iberian Peninsula system on April 28th was the occurrence of inter-area oscillations. So here, what I bring is a fundamental analysis on which is the impact of synchronous compensators to inter-area analysis. The first interesting thing to note is that, well, if we have a synchronous compensator connected to an infinite bus, we have an electromechanical oscillation, as we have with a synchronous machine that is supplying active power. The good news is that this electromechanical oscillation is in general very well damped, as you can see here from the eigenvalue analysis of the model of the synchronous compensator. But there is one interesting thing, and it's that this oscillation, the natural oscillation of the synchronous compensator, cannot be damped acting on through the power system stabilizer. Why? Because the capability of acting through the power system stabilized loop depends on the cosine of the rotor angle. And as the rotor angle of a synchronous compensator is equal to 0, the cosine of 0 is 1, so we cannot do anything. Okay, so let's see what happens with when we have a synchronous compensator tied to a synchronous generator. What can we do to damp the oscillation of the synchronous generator? Okay, what we can do is, in this situation, we have two modes. We have two modes. We have a mode in which the synchronous compensator and the generator oscillate against the rest of the system, and a mode in which the synchronous compensator and the synchronous generator oscillates one against the other. Okay, so we can try to design a PSS for the synchronous compensator. Well, if we had only a synchronous compensator connected to the infinite grid, we can do anything about the oscillation. But using a PSS of the synchronous compensator, we can damp the joint oscillation of the synchronous compensator and the synchronous generator against the grid. And what we can see is that, having a look on the eigenvalues, on the electromechanical eigenvalues, as we can see in this table, is the eigenvalues 1 and 2 became very well stabilized due to the action of the PSS. Okay, well, these are the fundamentals. The fundamentals is that, well, if we have an oscillation of the synchronous compensator, we cannot do anything. But if we have a synchronous compensator and a synchronous generator, now the synchronous compensator can do. Well, in Spain, the compliance of the grid code is checked through a standard that has been set up by the Spanish TSO, which is called the compliance standard regulation. And in this regulation, they have defined a kind of test systems that must be tested through simulation to verify the ability of the controls to damp the inter-area oscillations. On the first test system, which is a two-generator system, when you propose to incorporate a synchronous generator, you must check that the oscillation is well damped when the reactance between the buses number 2 and 3 increases. This is an approach to change the frequency of the oscillation. And you must prove that all the eigenvalues, all the modes have exhibit a damping greater than 15%. If you have a power park module, you have to check that there is no negative effect on the oscillations. And this is done through the test case at the bottom. So here we have a comparison of what happens with both test cases as we increase the reactance between buses number 2 and 3. And what we can see is that with the controls, with some standard controls of a power park module, we can, even without no additional PODs, just to increase the damping, which is the case that it's plotted in pink. And what happens when we add a synchronous compensator? Okay, if we add a synchronous compensator, we are in between the two cases. So what is the conclusion of this? The conclusion of this is that synchronous compensators should be equipped with power system stabilizers to contribute to the damping of the oscillation and let the situation be as we had before. So that's the main conclusion. We need a PSS also for the synchronous compensators. So let's go to the conclusion to have some time for the questions. The first part of my presentation was related to the stability of wind generators, and what we have seen is that the synchronous compensators can contribute to the stability of wind generators as affected by the stability of the PLL. And this contribution is robust with respect to the type of generator. We have assumed standard controls with a standard design approach. And related to the damping of the inter-array oscillations, the message is that although the synchronous compensator cannot damp its own oscillation, electromechanical oscillation, if it is equipped with a PSS, it can contribute to the damping of the system oscillation, in which there are more devices involved. And I think that concludes my presentation. Thank you very much.
Okay, thank you very much, Luis. A very interesting presentation. Now we have 10 minutes just for questions. Yeah, okay. Please introduce yourself before asking the question. Thank you.
Good morning, Stefano Lodetti from the National Physical Laboratory, the UK. Thanks for the presentation. It's very interesting, and I wanted to ask, I have two questions. One is a low level and one is a higher level. The low level is, if your models have been validated, so the results that you've shown, are you confident that then in practice will be according to your modeling? And the higher level question is, with increasing complexity of power systems, power electronics that can change the impedance of the system all the time, are we still confident of our models? Do we need to improve the details of the models we're using? Do we need further validation? Do we need better validation of the models, or are we still happy with the level of modeling of the system that we have? Thank you.
Very, very good question. I will go up, I will start with the high level. Well, one of the main problems that we face today is the use of the models. Now, TSOs request typically, let's say, closed models. They are proprietary models. But one thing that is happening is that although the manufacturers provide those models, the TSOs cannot use them in practice. They are so complicated. They are validated for a very simple case, single machine, infinite bus, but once you try to put them all together in a complex model, in a big system, you cannot run. We have lived the experience just of using a proprietary model of a manufacturer just to represent in detail a big wind farm, 200 machines, and the model failed. They cannot provide it. They run into numerical instabilities, so on. So there is a big problem with proprietary models. So to my opinion, the solution to this is to use generic models, but very well validated. So the problem is not to have a very detailed model that has been validated, but you cannot run in a system, in a big system environment. I believe that the solution is to develop generic models and to validate those generic models that should be open and should be based on the fundamental equations. Sometimes manufacturers say, oh, I don't disclosure because here, this is my knowledge. Please accept it, this is bullshit. To me, this is bullshit. You know, the equations, the knowledge is very well known, is in the books, and you are using the books to design your controllers. What makes the difference, there are some details that are not in the books that your device works. But the fundamental models are in the literature. So I bet on generic models that can be, the performance can be explained to the settings of the parameters, etc. Okay, so that's the first, the upper level. I must say that these models that we have not been validated. We have validated other models that we have had the opportunity. Last year, I spoke about variable speed hydrogeneration that has the same type of models. And recently, we have succeeded on validating those models. So I believe that these models are reasonable. Of course, they rely on some controller design criteria that normally the manufacturers do not disclose. But just, in the case of the variable speed generation that we have recently done the job, well, these physically based models work very well, and we were able to match simulation with the measurements. So this is a big issue, and it's important that we must move from proprietary models, closed models, to generic models, open models, so you can check what is the impact of a certain parameter. And this is definitely a very, very timely question. Thank you.
Thank you very much. Any other question? Okay.
Thank you, Luis, for the nice presentation about the synchronous compensators. I have two questions. One made by a colleague of mine who is following online the presentation. Apparently, they cannot, made the question, so I'm making a question on behalf of him, Juan Mauricio, who you know, and then another personal question. So the first question by Juan is concerning which models are you using, electromagnetic or electromechanical? Because he says he has seen a very high frequency in your Nyquist diagrams, so apparently those high frequency cannot be, for instance, with PSS obtained with electromechanical models, so I don't know.
Okay. In the first part of the presentation related to the stability of the wind generators, we are using electromagnetic models. Electromagnetic models in, at the fundamental frequency in the DQ axis, but we have the dynamics of the grid. In the study of the inter-area oscillations, we are using electromechanical models. But to study the stability of the PLL, we use electromagnetic models for both the wind generator and the synchronous compensator itself. And for the study of the inter-area oscillation, we use electromechanical models.
No, okay, thank you. Sorry. Now, my personal question is a philosophical one. I am quite, I will not agree with you probably, or you will not agree with me in this sense, but I'm quite skeptical about the need of using synchronous compensator in the long term. Maybe a transient solution, but not forever. I mean, if we all agree that we have to decarbonize the power system, and in many systems we will reach 100% of, renewable, you don't have nuclear. So probably the only rotating machines in the future will be hydro machines, the only ones, and many countries don't have hydro machines. So what I mean is that inertia and this kind of feature already enjoyed by power systems throughout 150 years is kind of being obsolete in the future. I mean, we will, of course, we will have a frequency or AC system with frequency and the like back, but inertia will be a local feature of an individual machine. It will be able to recover synchronism or not with the rest of the systems. So what I mean is, which kind of service provided by synchronous compensator will not be provided in the future by batteries or other power converter interface, except for the high short circuit current. Except for this, any other thing I think can be provided by future power converters arrangement. And then we probably will not need synchronous compensator. This is a personal reflection that probably you don't agree with me, but just to know your opinion.
No. Well, to that question, I have a high-level answer, and then I will go to the detail. Well, I think that what makes a difference the old power system and the new power system is that in the old power system, we had some services that were free. Inertia was free because there was was an inherent capability of the machines. And you don't have to pay for that. And what makes the difference is that in the new power system, if you want to emulate inertia, you need to pay for it. Why? Because you need a spare capacity in your devices. In a synchronous generator, you don't have to pay for the spare capacity. Let me just go back to one of my first images of today. On the left, we have the response of a nuclear station in Spain in the event of July 24. It was operating at full load, the valves fully open. No more active power was able to be extracted from the reactor, from the turbine. But the frequency drop came, and the machine naturally gave to the grid that power. But if we want to do in the new power system We can do, I'm sure that we will be able to do it, but you will have to pay for that. So, yesterday you were saying that we are moving to an economy of zero marginal cost. That's true, but you will have to pay a lot for the ancillary services. You cannot say to the people that as we don't have fuel cost, the cost of the electricity supply will be zero. You have to pay for the ancillary services, much more than you are paying today. That's the truth. That's the truth. You will have to pay a lot for the ancillary services. Now the big concern for the grid-forming converters is the storage capacity that the TSO are requesting for free, Come on. No, you have to pay for that. Let me just relate it to the blackout, which was not an inertia problem, was most a reactive power problem. Now, the grid codes request a huge capability for generating and absorbing reactive power. And, if you go to the Spanish system, we don't need reactive power supply capability because the grid supplies a lot. Why do we have a spare capacity to supply reactive power? Because it was a mandatory request by the grid code. We need markets to assign resources efficiently in the economy. In a liberal economy, the way to assign resources is through markets. And that's the main problem. And I think that it's very dangerous to say, you have to supply this service mandatory and for free. Come on. I think this is the main discussion.
With you, I mean, it's you need, of course, to pay for grid services. Of course, I totally agree, and this will be a big difference with the past. Even primary frequency regulation should be paid for, not only, of course. And in addition to what you have said, another big difference between the old system and the future system will be the distributed nature of all resources. There will be thousands of smaller plants, where in the past we had 100 big plants. So now, currently, we have probably 5,000 plants, including small PV and not rooftop, just grid connected. And all of them could provide reactive power support. All of them, if you are asked to do that. But currently, they are not doing it. So if we have had this service provided by renewable, that technically is totally feasible, we probably wouldn't have had the blackout the other day. So without synchronous compensator, just because just reactive power can be given if you have the converter has within the thermal limits, of course, the converter. So this is the idea. No? So
I think that the key issue is not the capability that you have. The key issue to me is you need a control system that extracts all the capabilities of the devices. Let me just to bring another example from the nuclear world. One of the Spanish nuclear stations, when it was put in service, the plate was 975 megawatts. And now the same station is providing 1,092 megawatts with many modifications, without many modifications. Why they were able to extract almost more than 10%, almost 20% of the capability? Because they were able to tune the control systems. So the challenge today is to implement and to tune control systems that allow us to extract all the possibilities of the technology that we have in the system. So this is the real challenge. And well, if you recognize which is the challenge and which is the problem, you will put the efforts on that. And that's the clear point. Just to implement control systems that are able to extract all the capabilities of the technology.
Yes. Thank you.
So we have to finish. Thank you very much for the presentation, Luis, and for all the questions. Okay. Luis, en términos de valor.
Okay, good morning. My name is Miroslav Chomat and I'm from the Czech Academy of Sciences. I'll be chairing this session. We have a slight delay, but we will try to keep up with the schedule. So I would like to introduce the first or author of the first presentation, Mr. Lopez. Okay, so the floor is yours.
So, good morning, everyone. My name is Luis Lopez. I'm at Concord University in Montreal. So, this paper entitled Grid-Connected PV plus Battery AC Nanogrids with EV Integration for Increased Resilience was part of the work of Mr. Mohammed Ali Gadari. So, he did a master's under my supervision. So, the outline of the presentation is as follows. So, we have a brief introduction. Then we talk about this future building laboratory, FBL. Then the main system components of this FBL, the experimental setup we used for the paper. Also the energy management strategy that was implemented, test results, and then the conclusions. So, well, as we have seen a lot, there are several concerns about the environment and the production of energy to supply our demands. Okay? Solutions go through renewable energy, and net zero energy buildings. So just to remind you that these net zero energy buildings are buildings that can provide all the energy they consume during a year, okay? So not necessarily at the same time, but well, you know, whatever energy they consume, they produce, okay? And also the electric vehicles that we are usually concerned about how to supply power to them. What we want to do is to use the energy they have in the batteries there. Well, resiliency and the power outages in Canada. So here we have to the left, okay, the reported number of outages in 3 regions of Canada. So Eastern Canada in blue, Western Canada in orange, and in gray we have this Central Canada where we include Quebec, my province there. Okay, so we can see that in general the number of power outages are increasing there, and then it's important to make sure that we can deliver power to the loads and to the houses. And during these power outages, that can be due to this extreme weather, wildfires, as well as overloaded power systems. Well, the FBL, so we have this project with colleagues from this Building Civil and Environmental Engineering. This is funded by this Canadian Foundation for Innovation, and we have 3 main areas of research in this building there. First is these energy-positive building envelopes and integration with this HVAC system, heating, ventilation, and air conditioning. Then we have this intelligent building operation, and finally our area there from this ECE. It's the optimization of residential nanogrids with renewable sources and EVs. Well, this is the system that, the electrical system of the regional FBL. Okay? So we have a transformer here. Okay? So then we have this main service panel where we have these non-priority loads. So here in this block we have the battery and the PV inverters there, 3-phase from SMA. Okay? Now we have 2 transfer switches here. One is in case that we have a fault, so we would like to separate the SMA inverters from the grid so that we can supply only our priority loads here. Okay? Well, this second transfer switch was created so that in case the energy from the batteries and PV, right, is not available, then we can provide some power with this EV, okay, to our priority loads there. So one point is that this vehicle-to-load inverter here, it's a single-phase unit and cannot be paralleled either with the grid or with other units there. Okay? So well, here we have the main system components. So we have these Sunny Boy inverters, so they're the PV inverters. So we have underneath here all the specs, right? But in principle, we have these PV inverters. We have 3 PV arrays. We have these battery inverters here from Sunny Island. Then we have here this vehicle-to-load inverter. So this is a kind of low-cost inverter that was bought by a colleague here for some tests, okay? And then here we have this SMA data manager, which is for control and programming of these Sunny Boy and Sun Island inverters. And we have this IO logic here. So this IO logic element was included to create a logic that can allow us to change the operation of the system based on the state of charge of this stationary battery here. Okay? So we have this lithium battery here, and we have this Nissan Leaf. So it's kind of an old vehicle there, and just to remind that the energy of the battery here is kind of low here, kind of comparable to that of this stationary one. Okay? So, well, we have some sort of sub-panels here. We have controllable loads that we're using in the test. And here's the proposed configuration, right? So the idea is that now, from this Nissan Leaf here, what we would like to do is instead of supplying power through this vehicle-to-load inverter here directly to my loads, we would like to get this single-phase power and using this spare Sunny Island here. So we have a spare unit, and then we would like to use this inverter, connect to this AC to DC converter here to charge the battery there. So I mean, if we transfer the energy from this, the battery of the inverter, the EV, to the stationary battery, then we can supply this to a 3-phase load over here, right? So but for that, one thing that we need to do is kind of control when we connect these 2 elements here. So there is a relay connecting these 2 elements, right? And by the way, we can control the amount of power flowing here from this CTEC inverter and from the car towards this battery, okay? Now, the idea is that we're going to be using this data manager here, which is connected to all the SMA elements, okay, along with this IO logic to kind of control a number of relays that we have here. Because in terms of resilience, we would like also to kind of do some sort of load shedding during some cases, okay? So, well, the idea is that to implement this logic, we needed this IO logic here, this unit, okay? So here we have a relay that's related to the Sunny Island 1, that's the master unit of this SMA battery inverters. And that this will allow us to identify when there is a fault in the system there, a power outage, okay? So now we have this 24 volts battery that is used for powering the IO logic. And as we can see here, we have two main relays. One that's for the load shedding, okay, in case the energy of the battery is low. And then we have another relay here that to allow power from the EV to go to the stationary battery, right? But one problem that we have is that since this IO logic, okay, it's based only on the instantaneous voltage or state of charge of the battery, we have to come up with a logic that would allow us to identify if the state of charge of the battery is increasing or decreasing and what range it is. Okay? So we needed to use the logic of these outputs here along with the relays. So the details are in the paper there. Okay? So here, for example, we have just some cases indicating what happens in this normal utility grid. So all these outputs here would be out, okay? And even this IO logic would not be powered there, okay? So in this case, this relay here for power from the EV to the stationary battery is off, and my load shedding is on. There is no load shedding there. So in case that we have the state of charge of the battery less than this, right? So I mean, now there will be power flowing here from the EV to the stationary battery, and the load will be shed, part of it, okay? So here we can see that this is the two extremes of the combinations between the outputs of the IO logic, okay? Well, again, there is no time to go through all of this, but we can see that in case the system is fully operational, there is no power outage, okay? So both relays would be off, right? And then depending on the condition here, if the state of charge is increasing, decreasing, and in what range it is, right? We would have different combinations for those two main relays, right? Implemented to those two relays, 1 and 2, along with the IO logic. Well, we have a test here that the idea is that to say we have a power outage, and then the battery starts to discharge, okay? Then the load shedding will occur at 50% of the state of charge. Then the EV will be connected manually to the system, okay? So that we can charge the stationary battery from the EV battery. And then there will be a condition where the battery will start to charge again, okay? So the load ends up decreasing, okay? Or maybe there's more PV. And then the idea is that we would like at a certain point to disconnect DV, say we do not need power from DV anymore, okay? So, well, here there are some numbers related to the parity loads we have implemented, the PV generation, okay? And how much power will be flowing from the EV towards the stationary battery, okay? Now, one interesting point is that, as this is a shared facility, unfortunately, people from this build engineering were playing with the PV panels there because they are also extracting heat from the PV panels, and they were not available for us to run the tests. So what we did is we had 2 PV emulators, and instead of using 3 Sunny Boys to supply power to the 3-phase system, we were able to use only 2 of them. But then the connection of the Sunny Boys, the PV inverters to the system was different, right? So that's an interesting aspect there. Right, so now we have the final tests over here. So the idea is that at this point here, in the beginning, we lost the grid. There was a power outage there, okay? And we can see here that the state of charge of the battery starts to decrease, okay? As we mentioned before, we had that 80%, 50, 45, 40%. So to run a test with those values there would be too long. So what we did is we kind of reduced the ranges there. So instead of 50% to start with the load shedding. Now we are using 95 only to be able to get the results, right? So now here we have these curves showing some important values there. So for example, at this point we have power outage, right? And we can see that at this point, if I'm not mistaken, it's 95, okay? So this curve here, which is my loads, the secondary load is, my load is kind of reduced. So before I had the primary, secondary, now only the primary loads, okay? And then we see that at this point, kind of the discharge reduces here, okay? And at this point, we go to a condition where we have to turn on the EV to support the stationary battery. So we can see that as we reach this value here, the power from the EV to the stationary battery increases there, okay? Then in this case, due to the choice of the parameters, we can see that the battery, stationary battery, starts to charge again, okay? And in this case, we have my load being restored, and even with this restored load, the state of charge is still increasing there, okay? And as a result, we get that at a certain point, we kind of turn off the EV, right? So that's the main aspect of this presentation, right? So we can see in the conclusion that we came up with this logic for connecting the single-phase vehicle-to-load inverter to help the EV support the battery to supply three-phase power to the system there. Thank you very much.
Thank you. Thank you very much for an interesting presentation. Do we have any question? We have time for one short question, I guess. Okay, no question from the audience. Maybe I would ask, so I guess that your system is actually meant for just emergency use of the battery of the EV. So it does not actually, you are not concerned with the lowering the capacity of the battery of it, because it's probably just kicking in just a few times a year, probably. Or
right.
what's the...
Right, yeah. So, I mean, the idea is that we are only going to be drawing power from the EV, right? So when there is this high demand of power, so to help with the resilience, supplying my loads for longer times, right? And just to finalize, the SMA equipment that we have in North America is not the same that we have in Europe. So, you know, there are much more resources available for SMA equipment in Europe than in North America. So that's why we had to do some sort of improvisation there. Thank you very much.
Thank you again. And we have the second presentation here, which is about, well, PV panels and, well, removing the dust. Okay, so Mr. Nassar.
Thank you very much. I'm Nasser from Sultan Qaboos University. Today I'm going to present about AI-driven detection of atmospheric obstructions. And so this is mainly on the part of detecting sandstorms that would affect basically PV cells. And so just before I start, I would like to give a small introduction about my university. We came from Sultan Qaboos University, myself and Dr. Nabil, in Oman, established 1986. It has 9 colleges and a size of around 20,000 students. So, of course, GCC countries, although they are quite dependent on oil industry, but there is basically revolutionizing their basically power production and with the dependence on renewable energy, and that mainly goes to solar and partly to wind energy. And other reasons we have there is that we have abundant solar irradiance, economic diversification away from oil, that's what they are targeting. And also there is climate commitments and sustainability goals. Beside that, of course, we have low solar electricity prices in global tenders beside job creation. And here are just basically a sample of some of the initiatives that's being carried out in the GCC countries. So for instance, in Oman, currently we have the every second phase solar project, and that's targeting around 500 megawatts. And also there is a target of 30% dependence on renewable energy by the year 2030. And also we have in Kuwait, for instance, the Shagaya project, and also their national target of 15 to 20% renewables by 2035. Another mega project in UAE, it's Mohammed bin Rashid Al Maktoum Solar Park, that's targeting 5 gigawatts by 2030, and also targeting net zero by 2050. And also in Saudi Arabia, likewise, there's Vision 2030 targeting the production of 58.7 gigawatt renewable capacity by 2030. Now, beside all of these commitments and plans, there are some challenges associated with the dependence or basically producing power from solar energy. And the first challenge is basically dust accumulation that can, of course, deteriorate the efficiency of the PV collectors, and also the high temperature. In addition, water scarcity for panel cleaning, and that's, of course, because they are targeting basically vast area for those plants, and usually we have these vast areas in desert where we have scarce water beside high temperature. And the top three are basically quite challenging when it comes basically to managing mega projects. So just some examples. If you look at the first picture here, this is quite common scene that happens, not quite rare basically, from time to time in Saudi Arabia, and especially in the Gulf. And here's a typical project where we always have it in the desert. And looking at the geography of the region, that's mostly desert. So the populated areas are mostly at the coast, while the vast of it is basically desert, where we mostly have the, this kind of projects. And of course, when there is a sandstorm, then everything is going to change, and the maintenance schedule has to change as well. And of course, there are some challenges that are basically country-specific, as seen in this list for some of the countries. Like Oman, for instance, we have dry climate plus seasonal shamal winds and dust storms. And usually this storm comes from either Iran or Pakistan from time to time in Oman, while in Kuwait it comes from Iraq quite often. So this is a preliminary study basically for detecting sandstorms by using satellite imagery. And here we are going to use a structured 6-phase approach to develop an AI system. And it uses YOLO version 10 for object detection. And in this study, we are basing the source of the imagery came from Landsat 8 and 9. And so the different phases goes from collecting the satellite images and then labeling the different, basically, classes of obstructions, and then implementing basically the object detection YOLO version 10. And then, of course, it goes to the deployment. And this is going to come for a later stage. So here we are just focusing on this side, which is basically detecting solar storm. So here is just basically a quick model framework. It starts by data acquisition and pre-processing, and that's by collecting high-resolution multispectral images for the different, from different regions around the region, the GCC region, and then annotating basically the spots where we can observe some sandstorms and other obstructions, like for instance clouds and ocean obstructions, and then modeling and selection and training, modeling, selection and training, and that's by employing, of course, YOLO version 10. And then at the end, of course, it comes to the evaluation using the different metrics for the performance of the algorithm. And so here's just a sample of these images and basically the labeling of the different basically obstructions on the image. And here's, of course, we are using image label for this task. And then, of course, here is just basically the main 4 stages, which is basically first the annotation, and that's by identifying the different obstructions on the image, and then performing the basically the modeling using YOLO10, and then of course training. And here this is going to go 3-way by having 80% for training, 10% for validation, and 10% for testing. And the optimization here goes for the hyperparameters, which is learning rate, patch size, and the epochs. The model performance is based on the box loss, and that is, of course, the disorientation between the detected box and the ground truth box, and also the class loss. And that goes to the different, basically, identification of the classes. So we have dust, we have haze, or we have sheen obstructions. And so we're going to look at the misalignment between the detected, basically, classes and the actual one. And then for the final, basically, metric, we are going to depend on the mean average precision that's based on 50% of the ratio of intersection over union, and that's going to take the area under the curve of precision versus recall. So the precision is basically going to detect how much of the true values out of all true values, how much positive true values out of all true values detected. And the recall, of course, is going to look at the percentage of the true values out of all true values, either detected or not detected. And then we're going to look at the area under the curve of precision versus recall for those where we have intersection over union of the boundaries being 50% or more. And here's just basically a sample of for the labeled basically regions or zones and the detected one in the algorithm. Here's just basically, if you look at the performance after 10 epochs, we can see that the initial losses were very quite high. For the box loss goes for 3.74, for class loss 5.18, and then we can look at how the basically the decrease in the loss. So the misalignment goes lower, and on the other side, if we look at the precision, it goes higher at the 10 epoch. So just in discussion, we can see that YOLO version 10 model training results confirm effective prediction accuracy and also demonstrate strong potential for environmental monitoring. And that, of course, goes for the scheduling when we have, or for the infrequent scheduling when we have basically strong sandstorms, and also increasing the accuracy across metrics support the use in sustainable energy operations in the GCC. And of course here also SQUAT, basically if you look at it also represents a key advancement in smart solar infrastructure management aligned with national renewable energy goals. And of course this is what makes it advantageous compared to the localized detection basic strategies. Now, some key challenges that needs to be addressed is number one, the quality of the data. Of course, here we are dependent on the Landsat. That's less frequent for that region. But of course, if we go into the implementation, then in that case, we have to look for a source that is basically more frequent in reading imagery in that region. And also the technological limitations that need for robust computational infrastructure. And that goes, of course, with the volume that's going to be handled as well as with the frequency of those images. Economic factors, constraints, and inconsistent policy support hinder large-scale AI adoption despite the abundant solar resources. And of course, that goes to the application itself. So in conclusion, basically, we can see that the effective detection for YOLO version 10 deep learning model models this quite accurately. And also the model performance, if you look at the precision, recall, and the mean average precision, it gets improved over the different epochs. And also it's quite scalable and cost effective, especially that it is open source. And for future work, of course, mostly it's going to be on improving the quality of the images and also the frequency of capturing these images at the region. And then, of course, when it comes to deploying, that will have to be another stage on basically quantifying how much impact that sandstorm coming from any of the directions will impact basically the plant itself, or the performance of the plant. And of course, this goes also to expanding the studies to different geographical regions if this is basically proven to be effective. That's it, and thank you very much for your listening.
Thank you for a very interesting presentation of this use of AI. Do we have any questions from the audience? Okay, over there. Do we have a mic?
Just one curiosity, it's a very good presentation. What about the source of images? Are there providers, and what is the impact of the point of view of economical values of the satellite images?
Sorry, I'm trying to get the...
You need satellite images to elaborate, yeah. Is there some costs for this images or not?
Some source?
Yeah.
Yeah, the Landsat is basically open source.
Also, the source of images is open and free?
Yes, exactly. Okay. Yes.
Thank you.
A paid one, of course, will be more frequent, and the resolution is going to be much higher.
Any more question? If not, I would like to thank you again.
Thank you very much.
And the next paper is actually associated with this one, I guess. And I would like to ask Mr. Nabil to come here.
Hello. Okay. Good morning. My name is Nabil Rawahi. I'm the same team as my colleague Dr. Nasser, and this is our student Mohamedou. So the title is similar to, or the topic is similar to what my colleague Nasser mentioned, but in this study we are not using images, but we are trying to use satellite data so that we will predict a common or normal sand or dust accumulation on the PV shells. So it won't be online, but it will be like we are using data of 5 years to see how can we normalize it so that we can schedule cleaning of the PV cells more efficiently. Well, this is the same slide as my colleague, so I won't go through it. Oman, this is Oman here, and as my colleague, thank you. And as my colleague mentioned, we are surrounded, or in the west side here, we have the empty water desert, so it's a good source of sand. We also have sand from Pakistan and Iran also. But at the same time, Oman is also blessed with very high solar or receiving solar energy. So it has an excellent solar potential, but the dust accumulation affects the efficiency of the PV cell panels. And what makes it worse is the water in Oman is not that much. So Oman is one of the arid regions. So we cannot use, just water every time to clean the PV cells. So it leads to increased maintenance costs and so on. the factors that will affect the sand accumulation as known tilt angle and spacing, which we can control, but there are other factors, wind speed and direction, and the particle sizes that we don't have any control of it. We can solve that partially by dust shields, nano and hydrophilic coatings, and active electrostatic dust removal systems. These will help, but again, the water scarce area as Oman always have a challenge of dust accumulation. And this is known, so there is always a tendency to have scheduled cleaning, but in that scheduled cleaning, the regional differences in the dust composition and particle size are not always taken into account. That will lead to a generalized solution that don't take account on the specific region that we have the solar cells. And the predictive models, they often neglect the dynamic environmental factors that will result in inefficient cleaning schedules. So the objective is to address the dust-related performance issues in order to have better quality in solar PV cells. And the approach is to use satellite data for real-time, region-specific dust monitoring, and integrate them into computational tools to predict and optimize the cleaning schedules that will hopefully provide a cost-effective practical solution to dust-prone environments. The data source that we selected the MERA2 original data from 2020 to 2024, combined with the data from PV systems in Oman, which turns out it's not that useful, but I'll mention that later maybe. So the data collected, the AOD, atmospheric parameters, PV performance metrics, and so on. So that was the first step. Pre-processing, of course, we need to clean and filter the data and get what are the engineering features that we need from these data. We use a neural network to train predictive models with engineering features, incorporate the seasonal patterns and spatial probabilities, so that we have different, we divide Oman into different regions, and link this to the PV performance that we got from the PV power plants that we have in Oman. But then connecting these two were not that easy, because the performance of the PV cells have also other parameters that will affect them. So we compared prediction with the real data from Omani solar farms, but the link between these two was not that strong. Because of the other parameters that affects the performance of the Omani solar farms, and but we evaluated the accuracy also using statistical data. So we integrated the model, or started to do that, but still it's under processing. And and the purpose is to provide actionable recommendations. Okay, this is still it's under work. This shows here the relation between data, the input data, to make sure that what input data are related to each other, and they're almost independent. All data are independent. After the training, this is the result of the prediction, which looks okay. Going to the conclusion, the dust decomposition model showed relatively high accuracy with 88.6%. The dust mass model had lower accuracy of 72.1%, but still this is better, we believe, than just going through the normal the normal cleaning of the PV cells without any data. And the result shows that there is a significant variation by month and day. Okay. The future perspective is that to refine our model, use more factors like wind, dust storms, and the geography. Real-time monitoring, this is a main thing. Real-time monitoring to integrate models into live system that can predict or measure the dust accumulation. And I saw yesterday, I think, one of the posters talking about cheap sensors to measure the dust accumulation, which can be a good point, I mean, to collaborate. And the result of this, hopefully, will be to optimize the cleaning schedule, and then we scale into wider area in the MENA region. So that's all from me. Thank you for your attention.
Thank you. Do we have questions? Okay, over there.
Hello. Hello. Thank you. I have just two questions. First one is, do you have some results on the validation of your data with experimental results? This one is the first question. Second is, actually this problem exists in a lot of countries, including our side. So that in economical point of view, so if you are using some specific coatings on PV modules, how it will affect to the cost of the module, and by using of these technologies, you are earning or improving the output from the PV modules, and if compare these 2 points, how the results will come out. Thank you.
Okay. So the first question was results of validation, right? Again, so what we did, there is no, we saw that the validation with the ground data, you mean? The actually measurements? We didn't do that because we don't have ground data. So what we did is just validation within the data that we have. So that's your first question? Yeah. Second one, I'm sorry, I didn't hear it very well. So you're saying that how this model, would it be economical to be used in other areas, or was that your question? Okay.
Okay, thank you. Because we are a little bit behind the schedule, I would like to thank you again. And the next paper is about connecting photovoltaics in residential areas, and it will be given by Dr. Simonetti.
Good morning, Mr. Chairman. Good morning, all. I present this work that we are having in our university about the connection of solar panels into the residential feeder and to see what it's happened if we are using phase-to-neutral connection or phase-to-phase connection of the solar panel. First, we have a little delay of connection of the solar panels in Brazil respect Europe, no? But it is experimenting a big increase in the last few years, no? We can see by these two graphs, the left one is of all the country. On the right, you have the increase of prosumers in my state, Espírito Santo. What happens? What happens that all inverters, solar inverters connected, are basically of 220 volts. But Brazil has two kinds of voltage supply voltages. We have some countries, the red ones, that the phase to neutral is 220 volts. But the others, the rest of the country, the phase to neutral voltage is 127 volts. So, as an economy approach, majority of solar panels are connected to 22 volts, 220 volts. Even if they are in the red part of the country, they are connected phase to neutral, or if they are in the rest of the country, they are connected phase to phase. What happens with the profile of the voltage along a residential feeder if we connect it phase in phase or phase to neutral? So the objective is to observe the consequence on supply voltages of the disordinated connection of distributed generators, solar panels, into residential feeders. No? If we allows the prosumer connect it into his point of connection, we don't get attention if they are connected to phase A, B, or C. We are studying about the voltage values, unbalance, and using simulations. A schematic to visualize what we are doing, it's very simple, no? We have the representation of the system by a voltage, an impedance of the system, and then the impedances between poles of the systems. No? We are considering 7 poles, and the impedance and the values of the system are shown here. We have studied many cases and extract some of them to show here. Mainly these 6 cases here. And the first case, what has happened normally without connection of solar panels. As the solar panel works only during sunny hours, we are considering the consumer of the residences during sunny hours. The consumer is very low. These values are here. Each pole, we can consider that the consumer is very low, 3 kilowatts active power and 1 kilovolt ampere reactive power. First of all, what happens if we are connecting without solar panels? The voltage profile is normal, no? It's very normal. The voltage decreases as the distance from the transformers to the last pole increases, but always into the limits according to Brazilian regulation. What happens if we connect a 10 kilowatts solar panel to phase A in pole 4 and phase AB, phase-to-phase voltage connection, pole 4. If you connect it to phase A, phase voltages presents a little modification, but not significant. Line voltages also. The same occurs for the line voltage. They have a slight modification, but it's not very important because the amount of power that we are injecting into the feeder is very low. And if you have the same power, 10 kilowatts, into poles 4, 2, 4, and 5, we are increasing the amount of energy we are introducing into the system, looking to the phase voltages, if you connect the solar panel from phase to phase neutral, the voltage of phase A, this one, here, the voltage of phase A increases above the limit of regulations. But if you connect between phase to phase, we have no problems with the phase to neutral voltage. On the other hand, if we have a look to the phase-to-phase voltage, connecting phase to neutral, the solar panel, we have no problems with the phase-to-phase voltages. But if we connect the solar panel into phase AB, in poles 2, 4, and 5, at the last pole, we have a problem with the limit of the voltage respect to the limit of the regulations of Brazil. The best situation, if you are connected just the 3 solar panels, one into pole 2, the other into pole 4, and the last one into pole 7, but mixing the phases which the solar panels are being connected, we know that we can see that we have a good behavior of the voltage profiling, considering both phase voltages or line voltages in both situations, connecting phase to neutral or phase to phase. It's the best solution to this situation. About the imbalance, when we have a connection into the cases, the poles are here and the cases are here. The voltage imbalance is very low. It's not a big problem, although in some situations they are above 3%. It's not so drastic about the connection, disordinating the points of connection. But the current presents a big imbalance value in some cases that we are connected, especially when we connect the solar panel in the same phase in all poles. Conclusions. The initial connection of solar panels in a residential feeder presents a minor influence on voltage profiling. As the solar panels increase, the connection of solar panels increase, voltage profiling starts to present a bad profiling and will get worse. And if the concentration of solar connections occurs in the same phase of the feeder, a technical solution for such cases is the connection to overcome this problem, is connection of a staticom. But what's the recommendation? The appropriate solution is to have control of the connection of solar panels along the feeder. And if necessary, ask the prosumer to change the phases of connection. Thank you very much.
Thank you. Any questions? Okay, if not, I would ask, is that motivated? Your study is motivated by real life experience, I think. Are there really problems with the unbalance in the system, residential systems, with caused by, well, this asymmetrical connection of PVs?
No, the unbalance is not a problem, but the voltage profile are experiment as in any country, are experiment an absurd increase in some phases along the day. So what's the solution? The solution is to verify the connection is being done in which phases and to change phases of the prosumer in order to make a better profile along the feeder. No?
Okay, thank you. And thank you again for an interesting presentation. And the last, but definitely not the least presentation will be given by Dr. Lopez Martin.
Thank you. Good morning. I'm going to change a little bit the topic. I'm going to talk about wind turbine towers and particularly how to monitor the condition of these wind turbines. I'm from the Public University of Navarra. We are working in this topic. And the purpose of the presentation is to propose an energy autonomous structural health monitoring system based on an IoT platform, and also how to use this platform in order to extend the lifetime of existing wind farms by monitoring the integrity of these turbines. This is the outline. First, a brief introduction, then the design of the IoT nodes, the energy harvester that is used to collect energy for the nodes, the operational model analysis algorithms we are using for this purpose, some measurement results, and finally some conclusions. Well, as you probably know, there is a problem with wind parks, that is that many of them are near the predicted lifetime, end of lifetime of this part. This is particularly a problem in countries that deployed early these technologies, such as Denmark or Spain. Many wind parks are approaching the end of the lifetime. There are some solutions that can be used for that. One of them is repowering the park, but this is expensive. Another solution is try to extend the lifetime of this park. This is obviously the cheaper solution. But in order to extend the lifetime of these parks, you have to be able that the wind towers are secure. I mean, that they are not failing. They are not prone to failures. In order to do that, you have to monitor the structure in order to make sure that the wind tower remains operational. In order to do so, you need to provide some kind of structural health monitoring system for the wind tower. This condition monitoring is not only needed for all wind towers, but it's also useful for new wind towers because it can also decrease the operational and maintenance cost of the wind towers. Normally, in wind towers, there's a mechanical load analysis that is done in order to prevent failures, but this is normally not enough in order to prevent the damages or the problems of aging of the structure, because it is an indirect estimation of aging. In order to face this problem, there's a standard is coming that is trying to regulate how to do the condition monitoring of these wind towers. But in any case, wind towers need to be monitored in order to analyze the condition of the structure. Not only the wind turbine, but also the wind tower and the foundations of the wind turbine. Typically, in order to monitor the condition of the wind towers, there are accelerometers that are placed in the tower and the nacelle. And also, sometimes they use different measurements, not only acceleration, but also stress or displacement. But acceleration is the main parameter that is used in order to detect problems with the evolution of vibrations of the wind towers. Typically, these accelerations are taken in two axes, the fore-aft vibration and the side-side vibration of the tower. With a three-axis accelerometer in the nacelle, the measurement is not enough, but at least it's satisfactory in order to detect many of the problems that may happen. In order to monitor the structure, the foundations and the structure of the tower can be monitored typically by one or better 2 or 3 accelerometers in the structure, but monitoring the blades is more difficult because blades are moving and because the mechanical loads to the blades are very high. But in any case, if you have accelerometers in the tower, you can indirectly monitor the blades because they are mechanically connected to the structure. This is not optimal, but it's working. The acceleration measurements have to be complemented with other parameters from the SCADA system of the wind towers, such as the wind speed, the rotor speed, the azimuth, etc. Collecting all this data and using adequate algorithms for model analysis, you can predict the operation of the wind tower, and you can detect in advance potential failures of these wind towers. So what is typically measured in these systems? Typically, what we measure is model properties of the structure, the tower and blades and foundations. Typically, what is measured is the mouth shapes, the natural frequencies of the mouth shapes, and the damping radius. The evolution of these parameters, particularly the evolution of the modal damping radius, can be a useful tool in order to predict potential failures in these wind towers. This is typical also for other structures, such as bridges, etc., in order to do this model analysis. But in particular, wind towers have some specific challenges. One of them is that the vibrations of the wind towers are of very low frequency and very small acceleration, so it makes it difficult to evaluate the failures, the potential failures of these wind towers. Also, they are complex structures because they have static and dynamic parts, and they have different operation modes that complicates the analysis. Another problem is that you cannot have a control stimulus in order to predict the failures. So you have to use what is called the operational model analysis, which doesn't need a specific source of vibration in order to detect the problems, the acceleration. Another problem is that the acceleration signals that are taken by the accelerometers are contaminated by harmonics coming from the rotation of the blades and some harmonics. So that makes difficult the problem of monitoring these wind towers. In order to solve this problem, we propose an IoT system that is based on some IoT nodes that are placed in the tower. They collect acceleration information and then transmit the acceleration through a gateway to the cloud, and we can do the analysis offline in order to predict failures using modified operational model analysis systems. This is the architecture of the IoT node with a microcontroller, the accelerometer, and we also provide an energy harvesting source in order to make the node energy autonomous so that we don't need to connect to a power source the node. The node is supplied by the vibrations of the tower that recharge the battery of the node. This is the IoT node we are using with a rechargeable battery. We are using an ST microcontroller of low power, 32 bits. The transceiver is using narrowband IoT protocol, and the accelerometer is this one with 3 axes and 20-bit resolution. In order to get energy from the vibrations of the tower, we are using an electromagnetic harvester that is collecting the energy from the vibrations. Typically, the problem is that for a typical wind tower of 5 megawatts, vibrations are less than 10 centimeters, the movements are less than 10 centimeters, and the frequencies, the vibration frequencies are less than 2 hertz. There are hundreds of energy harvesters for vibrations, but very few that are working with such small displacements and frequencies. So that makes the problem complicated. We designed a multi-directional harvester that is based on 3 masses, moving masses that are connected to a common axis, so that with the vibrations, these masses freely move. You can see this here for low frequencies, for slightly higher frequencies. And they have magnets in the perimeter of these masses and some coils around the structure that collect the energy. You can see here the structure. This is a cylinder. You have the masses here with the magnets in a half-back configuration and the coils around that collect the energy for that. And regarding the algorithms we are using operational model analysis, but in order to to adapt this model analysis to this problem, we have to modify the algorithms in order to adapt to the particularities of the wind towers and the IoT architecture. We have to remove all the harmonics for the rotation of the blades. We are using different techniques. I'm not going to go into the detail because we don't have time. And after removing these harmonics, we have to simplify the algorithm by decreasing the volume of data that is transmitted from the IoT node to the cloud. And in order to do that, we are using a random decrement algorithm. For instance, this is an example of the acceleration signal. This is the third harmonic due to the rotation of the blades that we are detecting in time. This is in frequency. And after detecting this harmonic, we remove this from the acceleration signal so that we can use this signal in order to estimate the integrity of the structure. We tested experimentally the system in a 1.5 megawatt turbine of 76-meter tower. This is the placement of the node in the nacelle. You can see here the harvester, for instance, with the power converters. These are the measurement results. This is the acceleration signals that are measured in blue and red. These are the two accelerations in two axes, the fore-aft acceleration and the side-side acceleration. This is a zoom of this acceleration signal so that you can see the periodicity of the rotation. This periodicity needs to be removed with the algorithms. And once this is removed, we can analyze this in order to do the structural health monitoring system. And in order to evaluate the harvester, we used the energy from the harvester to charge and discharge a capacitor. This is a charge and discharging cycle. And from this cycle, we estimated the power that is collected. The power that was collected was not very high. The predicted one was 91 microwatts, but due to the internal dissipation, the electronics is not optimized, and the converter efficiency that is relatively low. We use a very simple AC to DC converter. The measured power is just 17 microwatts. That is not enough to recharge properly the battery. This is because this harvester was not designed specifically for this wind tower, but we didn't have other wind tower at that time in order to test the system. But this figure has to be increased in order to properly recharge the battery. So that's the conclusion. Basically, we are working on a system in order to provide structural health monitoring of wind towers that is cheap in terms of cost, energy autonomous, and that can be useful, for instance, in order to extend the lifetime of these structures. That concludes my talk. Thank you.
Okay. Thank you very much for an interesting presentation. And do we have questions from the audience? Okay, if not, I would ask. You are actually processing the signals partly in the sensor itself to minimize the amount of data well, transmitted to the central. How you optimize this? Well, you need some computing power in the sensor, well, resulting in higher consumption and so on. So what's your approach to it?
Yes, thank you. That's a very good and critical question because the IoT node is resource limited, so the processing capability is very low. But at the same time, we cannot process everything offline because of the huge amount of data that we need to transmit. So the local processing in the nodes is based on what is called a random decrement algorithm. You have details in the references in the paper linking to other works that we are doing in this sense. And the idea of this random decrement algorithm is to simplify the matrix calculation that is typically done in order to perform operational model analysis. This way, we are able to decrease significantly the amount of data that needs to be transmitted without losing much accuracy in the operational model analysis algorithm. So that's the key point, is the reduction of the data transition because this random decrement algorithm that allows to adapt to the low capability of the nodes and to perform part of the computing at the edge node. Yes.
Okay, thank you. Because we are actually behind the schedule and there is a following online session of it, I would like to thank the presenter again and also the other presenters. And I would also like to thank you for a lively discussion. Thank you. Thank you. Very interesting presentation. All right.
Okay, so good afternoon, everybody. Partly present here and partly present online. Thank you for joining us at the conference. I will now open the poster session, which is online, of the conference. And I will start from the list with the first author that is listed in the program. The first paper is under the title Time Domain Assessment of Power System Stability in Case of High Share of Non-Synchronous Generation, Limitation Analysis of Electromechanical Transient Simulation. It's a group of authors from Hungary, so the presenter, please present yourself and you can start your presentation. Thank you.
Thank you very much, Mr. Chairman, for the introduction, and welcome everyone. I am sharing my screen now, and I would like to get a feedback if you can see it. Is it working?
Yes, nice and clear.
Thank you very much. Then I will start my presentation. As agreed, it will be roughly 7 minutes, so I would like to be quick and on point. So our research is about stability studies in power systems with high share of non-synchronous generation. And inside that research field, we focused on the time domain analysis of transients. And the hypothesis of this research was that by calculating RMS electromechanical transient simulations, we can make a mistake calculating the worst case scenarios. And we proved that by conducting in parallel EMT simulations, electromagnetic simulations, with more detailed modeling of power electronic converters to model the effects on the transients and catch the worst case parts of the transients. The KPIs for analyzing the transients was the rate of change of frequency and the frequency nadir throughout the events. So first of all, we started by analyzing the current literature and the state-of-the-art solutions in stability calculations. And we identified that due to the energy transition, due to the integration of the renewable energy sources, classical stability analysis methods, especially those which are relying on the electromechanical dynamics of the synchronous machines, are becoming outdated at some point. And this means that we need to check for new simulation methods, how to model the power systems. Also, there are new categories in the stability literature. So now, beside frequency stability, voltage stability, and angle stability, the traditional stability categories, we also can define resonant stability and converter stability, which are widely connected with high-speed transients, which should be modeled in the electromagnetic time frame. Also, there are some sub-cycle oscillations and rapid phase-locked loop interactions, which the traditional frameworks cannot capture. So, due to these changes, new modeling methods are required in the simulation field. And the problem is that there is an inadequacy in the current calculation methods. In general, we compared RMS and EMT solutions. RMS is currently widely used in practice, even by system operators, and it is good to capture the system-wide frequency dynamics. It is computationally efficient and quite simplified compared to the electromagnetic transient simulation, which also captures fast control dynamics. You can incorporate PLL and the inner current control loops and accurately describe the fault right-through as well during EMT simulations. And it is possible to do converter interaction analysis on that. So to quantitatively analyze these two simulation methods, we use the IEEE 39 bus system with varying level of inverter-based generation and we analyzed the frequency nadir and the rate of change of frequency throughout the simulations. And we identified a gap between the RMS and EMT simulations, which shows that our hypothesis was true in the beginning. So here you can see the outline of the system, the topology of the 39 bus system, which is quite common in transient stability analysis. Therefore, our research results are quite comparable with the available state-of-the-art. And we analyzed the different level of grid following inverters integrated, so 5%, 20%, 30% based on the total generation. We used the Silent Power Factory software to run the simulations, and we analyzed the center of inertia frequency throughout the process to capture system-level dynamics. The results showed that even a modest increase in non-synchronous generation led to a lower frequency nadir and faster rate of change. And with the EMT simulations, the effects are consistently more pronounced. This demonstrated that while the RMS methods offer computational efficiency, they may underestimate the transient impacts. The difference is not really large, but even in such a simplified environment which we used, there is a difference. So we can assume that in critical cases, so for example, with a larger level of non-synchronous generation, it becomes a more and more severe problem. And here you can see the center of inertia frequencies with different level of renewable penetration levels. This was the RMS simulation. So you can clearly see here that the frequency nadir becomes lower and lower in case of increasing more and more renewable. And here you can see the differences between the two scenarios also in the EMT simulation, and in the table we summarized that what is the difference between the RMS and the EMT calculations, and the hypothesis was that these are rather different in those cases. Thank you very much for the kind attention, and if you have any questions from the audience, I would be really happy to answer it. Thank you.
Thank you very much for your presentation. Are there any questions from the audience? Not from the audience, but I saw that some online questions are typed, but please type them in English so we can share with all the other participants here. So thank you very much. Since there are no other questions, I'll thank you once again for your presentation, and we move to the next author. Thank you. The next paper is entitled Modeling of DC Asymmetrical Faults in Bipolar High Voltage DC Links with Metallic Return by a group of authors from the University of Carlos III from Madrid. So are there any authors available for this paper?
Yes, I'm here. Hi.
Okay, thank you very much. Introduce yourself and you can start with your presentation. Thank you.
I am Carlos from the University Carlos III Madrid. Can you see my presentation? Can you see?
Yes.
Okay.
Yes, we can see.
Thank you. So I'll start. Well, I'm gonna present work titled Modeling of DC Asymmetrical Faults in Bipolar HVDC Links with Metallic Return. The motivation of this work is the increased relevance of this type of links to connect offshore wind farms to mainland and to connect islands to mainland and strengthen their grids. What we have developed is a compact and versatile model that's able to simulate asymmetries in the HVDC link, and also that it can be integrated in a software framework to perform RMS simulations. In this diagram, you can see the model, which is the central part. This would correspond to the HVDC that we are presenting. And also we have 4 converters connected to it and AC lines with generators, AC grids. The model consists of 3 lines modeled with the P-line model. And after resolving this circuit, we get two matrix equations. These are dynamic equations that model the system. One regarding voltages at the nodes and the other one regarding currents at the lines, which are the state variables of the model. The input variables are the currents of the converters, which we have four. These matrix equations have the matrices defined here, and I want to bring your attention to the matrix F, which is the one that models the faults. If you want to simulate a fault, you put the conductance of the fault in the corresponding place, and you can simulate the fault. We have 8 types of faults we can simulate, organized in 3 categories. Pole to ground faults, pole to pole, and pole to neutral. Of these 8 types, we're going to present two faults in the results. But first, I want to speak about the software framework, because one of the keys of this model is that it has been integrated in a software framework that is modular. You can see in this picture different models which correspond to this system. The HVDC link model we are presenting, and also model for the converters, for the AC grids, and for the generators. And apart from this modularity, the software framework has another key characteristic, which is the automatic flash start initialization, which enables the configuration of new steady cases easily and quickly. And finally, I'm going to present the results. We have 2 simulations. The first one is a simulation of a fault at node A+ to ground. It's an asymmetrical fault. We can see here in this graph the voltages, which suffer a voltage dip during the fault. And also we see that the voltage at the neutral acquires negative value. The negative pole is only slightly affected. Here we can see the currents at the lines. The positive line is the one that suffers the short circuit, so the current is reversed in direction to supply to the short circuit, and in the neutral has to compensate for the change of current in the positive line, so it acquires a lot of current. In this final graph, we see the currents in the converters. In purple and yellow, we see the currents at the converters connected to the negative line, slightly affected, and more strongly affected are orange and blue connected to the positive line. In the second simulation we have performed is a pole-to-pole simulation, which would be from A+ to A-. This is a symmetrical fault, and we can see it in the results here in the voltage. The voltage dip takes place at both poles, and in the currents, the current reversal also occurs at both lines. We can see that the neutral is barely affected in the simulation, while in the previous case, which was an asymmetrical fault, the neutral had a more relevant role. So the conclusion that we draw is that if you want to simulate asymmetrical behavior, it's very important to simulate and to model the return path to have an accurate simulation. And to sum it up, we built this model. We have a software to perform simulations, and we will keep on working, especially on the control of the converters connecting AC grids to DC grids. Thank you for your attention. If there are any questions, I'll be happy to answer them.
Thank you very much for your presentation. I would like to ask the audience, are there any questions? No? Then thank you very much once again for your presentation. We will move to the next paper.
Thank you.
The next paper is entitled Analysis of Low Frequency in Offshore Wind Inner Array System. It's an author from the University of Basque Country. Is the author available online? The author is Inaki Arambide. Okay, if not, then we move to the next paper. The next paper is Applications on Power System using High Voltage DC Voltage Source Converter Technology, also by the same author, Iñaki Arambide, from the University of Basque Country. Is he online? Iñaki? If not, then we move to the last paper scheduled for this session, Mathematical Modeling of Renewable Energy Communities for Energy Economic Assessment, by a group of authors from Hungary, from the University of Technology and Economics. Please introduce yourself and you can start your presentation. Thank you.
Yes, hi, hello, good everyone. Can you hear me? Can you see my screen? Great. In that case, hello again, my name is István Vakony. I do have the privilege to have a short overview regarding my PhD students' work, our common research, which is called the Mathematical Modeling of Renewable Energy Communities for Energy Economic Assessment. From one side, yes, it's absolutely a technology-driven activity, as you can see later during the presentation. But I really like this research topic because it's absolutely a complex problem and complex solution. Because not only technology-wise and technology part should we find a proper solution, but from economic point of view, it should be suitable. And the rate of returns, everything else has to be matched. Without that, it won't work. And of course, the regulation part is a crucial point in that aspect, because there is an umbrella regulation coming from the European Union and based on the EU laws and Fit for 55 and everything else, and somehow it has to be translated on a national level, and on national level we have to find the solutions how to implement the visions and the viewpoints. So altogether, the energy communities consider a promising option for the deployment of the renewable-based local electricity generation they use in the EU, and it can be a key point. It can be a solution how to foster the renewable integration, follow the green transition targets on an appropriate and suitable cost level and with technology solutions. So we put together a business and mathematical modeling altogether, how to manage the differentiated solutions, because yeah, we can discuss about a single power plant with some energy storage. We can discuss about local environment institutions, or an industrial park itself, or condominiums or family houses. So from regulatory, technical, and technical point of view. So this is our dilemma in this situation. These approaches are in one part similar, but on the other hand, they are different. Which solutions and which approaches can be beneficial from the end user point of view, the other stakeholders, for example, the distribution system operator point of view, the trader point of view, and of course the regulatory and the national wise or the EU wise targets point of view. So put everything together, there are some central elements. For example, the community has a central higher capacity solar power plant, for example, and there's central energy storage. There are operating principles, and there are the energy storage strategy, how to implement the new technologies into that environment. It is really important to highlight that the whole model and the whole concept is not about how should I say, just for fun implement technology solutions. So the technology in itself can't be a good or a wrong approach. We can utilize on an appropriate way a technology, or we can miss the possible added values. So we tried to force the whole business model consistency into that level that how can we provide the maximal added value for all of the stakeholders. And from that saying, you can already feel that it is a multi-optimization problem. And that's where I would like to turn out that the modeling cost and revenues are the key equations in the whole mathematical modeling. So the model analyzes the costs, for example, grid purchase, balancing energy, operational, or we can discuss about TOTEX volumes, and the revenues should be determined the total cost of the whole community itself. And based on the optimization way of working and the method, we put together in my understanding, a quite valuable concept, because it's not only a concept and a theory, but we had a project last year with one of the largest energy company in Hungary, and we forced that into a proof of concept and the pilot, and establish working energy communities based on that approach, but mainly Bavarka worked out. One result from the many numerous simulations. So the diagram shows an optimized one-day operational strategy, how to fulfill the storage capacities, taking into consideration the economic behaviors and the economic aspects on the market. So not only day ahead and long-term contracts, but intraday market, and the PV generation itself. How is it possible to manage that perspective? And on the second diagram, you can see probably it's a little bit better. With this zooming level, you can see the numbers on the NPVs, so on the 10-year term, but all these parameters are possible to recreate. So the concept is defined something, but how long we should do the analysis, what kind of asset parameters can we take into consideration, are all of them possible to change or replace or rethink. So at the end, you can see from many running simulations on the diagram, the net present value is a function of the combined effect of the inflation, of course, and the annual electricity price increase. And it can illustrate the increase in either factor strongly improves the project financial viability, and a suitable combination of, in that aspect, the two necessary incomes and factors. And we can provide many more. It depends on the applicable situation. So as a first step, we define a possible and implementable NPV, so focusing only on electrical energy, but we let it open to heating power, transmission power, and every other dimensions of the power usage to fulfill the modeling of the whole concept. So one more minute and I will finish, because I know that the time is running. So highlighting from the end result and the conclusions, we can say that this mathematical model is an effective decision support tool for the energy economic assessment of a planned renewable energy community, not only for electric, but later on for other dimensions as well. And with the methodology what has been worked out, we can easily define the population of the energy community and test the possible new technologies in the environment. In a nutshell, that's all from our research, and I'm open for the questions and comments. Thank you.
Thank you very much for your presentation. Are there any questions from the audience?
Yes, I would like to raise a question. Thank you very much for the great presentation. My question may be a little bit out of scope. You mentioned that in the European Union, energy communities are really important. How is the situation worldwide? Because you were quite focused on the EU regulation. Are there any in Africa, in the US? What do you know about that?
Thank you for the interesting question. I would like to answer it from two folds. From one side, we are focusing on the EU regulations and our neighborhood, and we should say that the energy community, it's a really new thing. It turned out in 2019 and so on and so on. This is not true. Almost 2 or since 3 decades, many energy communities are already working in operation, but we didn't call them energy communities. So if you go to Austria or Italy, you can find energy communities which are working since 20 years, but they didn't know about themselves that they are energy communities. So one side, we put a nice framework into that to handle it properly. That's absolutely a good thing. From the other side, what you mentioned, yes, there are some solutions outside of the EU regulation, but from per definition point of view, this is not an exact wording. What should we treat as an energy community in Africa or the United States?
Thank you very much.
Okay, are there any other questions? If not, then thank you. I would like to conclude this session. Thank you to all the online participants, authors and participants, as well as the participants in the room present here. So thank you very much to everybody, and with this we close session P3. Thank you.
everyone. Actually, we are late. Now the floor is given to Mr. Junio Quintero. Please. I actually wanted to ask all the authors, we're already behind the agenda, so to use effectively at the time.
Okay. Well, many thanks, Professor, and good morning, everyone. My name is Pablo Rillo Quintero. I come from University of Cádiz in Spain. We are the research group in sustainable and electrical technologies in Algeciras. And today I would like to present to all of you our work entitled Hierarchical Control for Isolated Microgrid Cluster under Renewable Variability. So this is my agenda for today. I will start with a motivation of our work, and then I will introduce the isolated microgrid cluster under study, and the core of our paper, which is hierarchical control that combines grid forming and grid following inverters for isolated microgrid cluster. Finally, I will present some results and the discussion of our work. Well, to start with a brief motivation, it's a fact that the modern power system is constantly changing. And nowadays, the concept of microgrids have emerged as an interesting solution to coordinate renewable energies technologies as well as energy storage system. With this increment in the number of microgrids, we can then arrange a number of microgrids and then build a cluster of several microgrids and to arrange like a campus cluster like this. This can be a microgrid cluster, or a hospital that can also be a microgrid, or of course an industry microgrid. When several microgrids are coordinated together, we need then to design a proper energy management system to coordinate all the records in an optimization way. So regarding microgrid cluster, there are mainly three key aspects that we need to take into consideration when we are operating in isolated mode. One of them is, of course, that when we don't have a main grid, we need then to coordinate the voltage and the frequency in standard mode. The second consideration is that isolated clusters are usually coordinated into a hierarchical control, like primary control, secondary control, and tertiary control, that all we know. And last, that is a very important fact, the variability and the dynamic of renewable energy technologies, as well as wind power or photovoltaic power, must be considered. In many works that the microgrids are based into voltage source inverters, the dynamics of the source is just modeled as a DC source. Okay, so a DC source, we lost the dynamic of the changes in the operation of power plants or wind systems. So here, our main proposal is to take into consideration the variability and the dynamics of rates and design a hierarchical control in an isolated microgrid cluster to manage all the resources. Okay, so here in this figure, we can see the isolated microgrid cluster under study. As we can see, this comprises 3 microgrids, okay, microgrid 1, 2, and 3. All the microgrids have the same configuration. It's a PV power plant, battery energy storage system, and a local load. One of the most important things in this work is the combination of grid-forming inverters and a grid-following inverters. Okay, so with these 2 microgrids, we are going to create a grid and to maintain stable here in the point of common coupling the voltage and the frequency. And with this 3rd microgrid, which is operating under a grid-following inverter, it will operate as a backup microgrid. So when we need more power than the power that are delivered by these 2 microgrids, this 3rd microgrid will operate to give the necessary power. Okay, we can also see other typical elements as the output of the 3 microgrids as RNC filter to mitigate the fluctuations at the power output. Also a power transformer to elevate the level of tension as the output of the voltage sources. And then 3 transmission lines to connect all the cluster together with several loads that are going to be connected and disconnected in almost real time. Our study is focused on dynamics, so we are taking into account a very short sample time into MATLAB Simulink, like 50 microseconds, because our idea is this work serves as an example and then integrated into real time using Opal. Okay, so this will be our first step in our work, and then our idea is to develop a more sophisticated model, but take this as a benchmark case. Okay, so if we move here to the core of our paper, you can see here the hierarchical control. As I mentioned before, it is divided into 3 levels: primary control, secondary control, and tertiary control. If we start here with primary control, we have 2 primary controls, like one for the grid-forming inverters and a second one for the grid-following inverter. The primary control for the grid-forming inverter is based on droop control, as you can see here, the typical equation and frequency and voltage for droop control, with the coefficients of droop, okay? The coefficients of the droop control technique. Our idea here is to generate voltage and a frequency, and then into a cascade loop, we are moving to a current control that will generate the direct and quadrature current reference from the voltage control. Here we are employing a feed-forward technique just to decouple the direct and quadrature components of the system. And then with this voltage reference, we can then employ a typical pulse width modulation to get the gates of the EGBT. Okay, so this will be the grid-forming primary control, but just in the following operation, we have just opposite the difference, because with a grid-following inverter, that we want to do is to inject a certain amount of power. So here we have a reference power that we are dividing by the direct voltage, and then we get the direct current reference and the quadrature reference of this scheme. This component, we can then all the same process and then generate the IGBT gates for the primary control into the grid-following inverter. Just for the secondary control, we know that some disadvantages occur just because operation, when the power demand increases or this decreases, and we need to restore the frequency to rated values. So here we are employing a PI control just to restore the difference and to mitigate the error between the rated frequency and the measured frequency. And in a tertiary level control, we have here in the top of our hierarchy curve, the power dispatch. We are here, active demand, okay? And regarding the available power in the 3 microgrids, we are then to get the droop control coefficients of the grid-forming inverter and the power reference for the grid-following inverters. Regarding the tertiary control, we are here presenting a very simple concept, but it's useful. We can use it many times, which is the available power concept in real time. Just is the sum of the PV power and the best power within each microgrid, so it is repeated 3 times, minus the internal load within each microgrid. So our idea is a proportional power dispatch, that the microgrid with a higher available power will deliver more power than the second microgrid. Just if we don't have enough power with microgrid 1 and microgrid 2, the excess power will be summed altogether, and then the microgrid 3, the microgrid operating just a grid-following inverter, will deliver this excess power. So our idea is that the microgrid 1 and microgrid 2 will be the main powers delivered, and then the microgrid 3 just will operate when we need an excess power. Okay, so if we move here, some results in this figure, we can see the 3 PV irradiation profile for the 3 microgrids, okay? We consider that low values from high values. Our idea here with this step is to test the control into extreme conditions, okay? With rapid change, with sudden change in in the radiation, and then see what's happening with the control and with the stability. Here in this figure, as we can see in a blue trace, the available power of the 3 microgrids, and in a pink trace, the delivered power. So it's obviously that the power delivery for each microgrid must be under the available power to avoid disturbances and power problems. So here we can see here in the middle of the simulation, as both microgrids just check the available power. Okay, it's matched the available power, and we also need more power. So in this scenario, the microgrid 3 is operating almost 100 and 200 seconds, and it's when the microgrid is operating. Here we can see also some results. Here the profile of the demand at the microgrid cluster level. And we can see the internal power dispatch within each microgrid. So the green trace will be the PV power, the blue trace is the battery power, and then the pink trace, which is the sum of these 2 traces. So as we can see here, when we have a surplus of power, for example, in this scenario, the battery is operating in charging mode, but also in other scenarios like this, that we need to give more power, like 100 and 200 seconds, we need to change the operation mode of microgrid 3 to meet the higher demand. When the demand is again low, at 200 or almost 300 seconds, we can see here that the microgrid 3 changed its operation mode. It's also giving a few power, as is the pink trace, okay? And then the microgrid 1 and microgrid 2, which are operating in grid-forming inverters, are in charge of maintaining the power problem. But what's happening besides the power problem? We need to maintain stability into isolated system. So here we can see frequency and voltage that almost look stable, okay? Don't say to have many disturbances, but are some confidence problems, like here, here, and here. So how to measure this problem? Well, it's easy. We have IEEE standard, which is this, that take the power quality of our system. So it said that we need to maintain the frequency between 0.3 hertz up and down, and the voltage under 10% of deviation. See here, the conflictive points here and there are within the safe zone, so it looks stable and the range, and it also happens the same with the maximum voltage and the minimum frequency. So we can see that besides the power balance is satisfied, also the stability problem is meeting with this hierarchical control. Just to conclude, I don't want to take more time. Some conclusions. So this hierarchical control, that it was based in a simple concept of the available power and the combination of grid following and grid forming inverter, was an easy but suitable solution to introduce into the control of several microgrid clusters, because we are now working in more sophisticated model, like 15 buses or 33 buses, and it also operates well with this concept of the available power and the combination of grid following and grid forming inverters. So regarding future works, our idea is to design more complex energy management system and focus on this as a benchmark case. So that was all for me. Many thanks for your attention. If you have any question, I'm open to question now. Thank you. 30 minutes.
Thank you, Mr. Quintero. We have time for just one question, please. Okay, that's fine. So maybe you will discuss in Colorado.
Okay, thank you so much.
Thank you. The next presenter, we have Ms. Romero Filguera. Okay. Please, welcome.
How can I share the presentation?
You did it?
No, I think so. Not here. Let's prepare. It's in both PDF or PowerPoint, if you want. If it's in PowerPoint, it's much better.
Which one?
I have 15 minutes, isn't it? So I will press the button. Don't worry. Okay, buenos días. Good morning. Good morning, everyone. Thanks, Professor. Well, in this presentation, I would like to show you this R&D project and the work and the research work performed within this project. The project is H2 Verde, which is part of the complementary plan of the Plan de Recuperación, Transformación y Resiliencia. And the work performed within this project is the decarbonizing an offshore microgrid with green hydrogen, the Plocan case study driven by H2 Verde project. I have to say that maybe this is not a huge academic work, but it's a real work. Right now we are installing this infrastructure in an offshore platform very close to here in Gran Canaria. And I would like to offer you this new infrastructure for your research work because it's our job, it's our business. So this is the index. I will go very fast. I don't know if you know us, but Plocan, the oceanic platform of the Canary Island, is a public institution owned by the Canarian and the Spanish government at 50%, so daddy and mommy, just a 50% for both, so we love both. And we are very close to here in Gran Canaria, in the coast. And the main goal of our institution is to help the development of the marine and maritime technologies and the know-how involved in marine and maritime issues. We have 23 square kilometers of a test site, of a marine test site in the coast of Gran Canaria, in the northeast coast of Gran Canaria. And in the middle of that test site, we have an offshore platform, which is a laboratory for observation of the ocean and even for other technologies to develop and to test and validate technologies related with marine research. This test site is, we have two power cables to export the energy of the prototypes deployed in the test site, up to 5 megawatts both. And we have the capability of export up to 15 megawatts to the grid of Gran Canaria. But at the same time, we have the capability of test, of validate small prototypes, and we consume the energy in a specific smart grid installed in the offshore platform. So basically, this is our house in the sea, and as you can see, it's not only for testing marine renewable energies, but also marine technologies in general. So this is a specific project, Energía Hidrógeno Renovable, I've already explained you, is a part of the Plan de Recuperación, Transformación y Resiliencia with Canarian funds and Spanish funds, and taking funds of the next generation EU funds. H2 Verde addressed the crucial challenge by decarbonizing the energy system by using renewable hydrogen and energy as an energy vector, especially critical in isolated system, as our Canarian systems. And we work on different action lines. The first one is related with the production of hydrogen with renewable energies, and the second one is specifically with offshore wind and other marine renewable energies. And the line 9, is the use of hydrogen in the industrial and domestic sector using hydrogen fuel cells. And basically, as I mentioned before, we have a smart grid, a microgrid within the offshore platform. This smart grid is a 1 megawatt smart grid, so it's not industrial size, but it's not a laboratory, it's not a small laboratory. The base power generation, I mean, the synchronous generation is powered by 2 diesel generator, two 508 kilowatts diesel generator. And the power generator sequence is, as you can see, first of all, diesel generators, and then the prototypes. Okay, this is a sort of plug-and-play infrastructure. So we have 4 positions up to 250 kilowatts to connect prototypes at the end. And those prototypes obviously normally need to see the synchronous generation through these 2 diesel generators. Okay, then the load supply sequence is auxiliary service of prototypes, the Osho platform's load demand, and then at the end of the day, if the surplus of the energy produced, obviously we are not able to consume all that energy produced by those prototypes. Right now we have to burn the energy, which is a pity, okay, in a resistor load bank. So with this project, we will install a part of what we have already installed in the platform. We will store electrical storage in lithium-ion batteries up to 864 kilowatts hour, so practically the capacity of the system. An electrolyzer, a 100 kilowatts electrolyzer with a production of 43 kilos per day at maximum power, obviously. And then a fuel cell. And right now we are installing a 55 kilowatts. It was cheaper than 50 kilowatts, so we decided to go ahead with 55. And then at the same time, we will install renewable energies as a baseline generation in the platform. We have not many space on the platform, but we can install some PV panels, some small wind turbines, just to cover at least the baseline demand of the platform, okay? So our goal, and this is something we are, which is happening right now, so we are installing right now today, is this H2 Verde plant. Basically, it's composed by one container with a full cell of 55. This is not okay. So it's a 55 PEM type full cell for the power to grid. Okay, for the power to grid to reinvert the chemical energy into electrical energy. Then we have an electrolyzer PEM as well of 100 kilowatts, and the H2 green storage. We will have 9,600 liters of hydrogen, which is practically 180 kilos of hydrogen at 200 bars. And then, well, basically this is the H2 Verde plant integrated in the Plocan smart grid. So right now, we don't turn on the electrical system of the platform 24 hours, 7 days per week. So it is on only when we access to the platform, okay? And basically, this is the amount of hours that we access to the platform. So 960 hours per year, which is the 11% of the year. Obviously, we have deployed a lot of observation sensors, and these observation sensors take the measurements, and then when we press the button on, we receive all the measurements. But it would be nice if we receive real time. Now it's not possible because we burn fossil fuels, so it's not okay. It's not something that is good, and we don't like it. But with those 11% of the year on, we will emitting those pollutants. Okay. With the first phase, we will install PV panels on the roof and also on the wall, on the south wall. It's not efficient, but it is the space that we have. And we will achieve a renewable penetration of 65.1%. But at the same time, we are able to stay on 24 hours, 7 days per week, which is very good for us, for our operation at the end. With the second phase, we will achieve 50 kilowatts PV panels, and we will install vertical axis wind turbines, small wind turbines, up to 12 kilowatts. And with this installation, we will achieve the 99.8% of renewable. Okay, this is for the first year, because the batteries are 0 at the beginning of the year. But the second year, we will achieve the fully decarbonization of the platform. So, with this second phase, at the same time, we will achieve something which is very important for our operation, which is to have the batteries at 100% the most of the year. And this is important for us to provide a synchronous generation for the prototypes that which are installed in the test site. Obviously, we have grid forming, StatCom, all that things that are very actual, because of the fact that 2 or 3 weeks ago, or 1 month ago, I cannot remember exactly, in the mainland. So, finishing, this is the comparison of the energy mix before and after. So at the right now in the current Plocan grid, we are producing electricity only with diesel generation, and obviously we are traveling to a very different energy mix. And obviously our main goal is to go to 0 emissions. And which are the benefits of the Plocan smart grid with H2 Verde project? Well, the battery charge at 100%. So it's very, very useful for us and for our users, because at the end of the day, if we, the users of the test site need the synchronous generation of the diesel generators, must pay the bill of the diesel, which is costly. The better grid stability due to lithium-ion batteries converters, much better grid stability, static and dynamic. The possibility of studying the generation mix of prototypes with the production of hydrogen or green hydrogen at the same time, and the 100% grid availability without cost, as I mentioned before, for the users of the test site. So this is a schematic our project, which is, as I mentioned before, which is installing right now today, and I hope to press the button before the summer. Hope so. Cross our fingers. And well, finishing, this is schematically the plant. This is our offshore platform, and this is basically the aspect of the H2 Verde plan. As I mentioned before, is for you, for the researchers, for the companies, for the R&D projects to use it. To install sensors, to install different things to study the performance of the system or their system. And the main conclusions, well, the first one is the full decarbonization of the Plocan offshore platform is feasible. This is feasible. This is obviously the first conclusions. 24/7 continuous availability of energy of the offshore plant, which is very important for my colleagues of the ocean observation, very important. Grid static and dynamic stability, grid forming and synthetic inertia. The generated renewable hydrogen will be used in several use cases, all related with blue economy, because it's our business at the end of the day. And well, we think that H2O Verde project contributes to validating hydrogen generation in marine settings and its integration in a small isolated system as our systems. It's not cheap. It's not cheap. The cost of hydrogen, I can advance you, that is 50 minutes, 40, 50 euros per kilo. It is what it is. Obviously, we have a lot of extra cost in terms of marine activities, because it's not the same thing to install an electrolyzer on land and install an electrolyzer in the sea. It is the first in Europe, I think, with marine energies, and obviously it's costly. The further research is to model different prototypes connected to the smart grid and to study the performance of the system through different scenarios. We would like also to study not only modeling, but in real operation. To model different uses for the green hydrogen beyond the power to grid, obviously. I have right now power to grid, but we would like to study power to X, etc., with other users, and to develop an economic analysis about the target Plocan smart grid, including net present costs, LCOE, LCOH. We've already done, and that's the figures, 40, 50 kilos, which is far away from that target from 5 or 4 euros per kilo. But for our platform as an isolated system, the NPC, for instance, and the LCOE is cheaper than we have already. It's cheaper than we have already. So thank you very much. If you have any question, please go ahead. 16 minutes more or less.
Thank you, Mr. Romero. Please, questions. Okay. So we'll have one question, then you will discuss in the couple of hours of the conference.
Thank you. Perhaps I missed the information, but I suspect that you need to desalinate the seawater for the electrolyzers, right?
Yeah, we have already an osmosis plant on the platform, so that's already done.
Okay, and it has some energy demand, so how does it affect the feasibility of the whole concept?
Yeah, this is included in the energy management system, yeah.
Okay, thank you.
But it's not so important. It is important, obviously. We have to take it into account, but normally people think that this is critical for the system. It's not so critical. The water, the necessary water is not so huge for the size of the electrolyzer, obviously. If we are talking about the scale up of the system, obviously, it is important to take it into account, but not for this system.
Okay. Thank you,
Mr.
Romero. So we have next presenter, Fioravanti. Okay.
Thank you, Chairman, and good morning, everyone. I am Fioranti Andrea. I am a researcher of electric power system of University of L'Aquila. I work together with the Professor Prudenzi from University of L'Aquila, the Professor of Electric Power System, and the Professor Ciancetta Fiorucci and Mari, Professor Electronic and Electric Measurement. In this work, we analyze the grounded system interference between a smart tunnel electric distribution system. We study the interference between this infrastructure, the smart tunnel, and the private ground system. What is the smart tunnel? It's called also the utility tunnel. It's an infrastructure posed under the street in the big in big city with more population. It accommodates key services such as optical fiber network, telephone network, power grid, drinking water network, wet sewage system, and black sewage system. Also, the gas pipeline system is put out of the smart tunnel or utility tunnel for the safety security. All systems are housed in dedicated accessible compartments, allowing technicians to perform self-inspection, execute efficient maintenance, and avoid the road excavation in case of failure. The advantage of smart tunnel is the simplificate the file detection and repair the fault, reduce the installation and the expansion cost, enable rapid upgrade the new connection without brought the street or the stone on the street. Because we speak of the smart tunnel, because it's installed, this infrastructure is installed in the L'Aquila city. L'Aquila city is have an earthquake in 2009, a big earthquake in the last year. In the last years, with the 308 dead and 66,000 homeless. In this earthquake, we have more damages, for not only the private building or national building, but also the utility network. For example, water, electricity, several telecom, utility were severely affected, causing service outage and complicated related effort. In the emergency, the government building the 185 private building with 4,000 apartments for 50,000 people in 9 months. After the reconstruction, we continue today the reconstruction. The cost for the reconstruction of buildings is between 2-3 billion euro. For overall damages is about 60 billion of euro for economy and other. And today is at 88% of the total of reconstruction. This is a real smart tunnel, utility tunnel implemented in the city of L'Aquila. We have the pipeline of, for example, water on or waste. We have the passage for the electric and telecommunication installed. This is in building the construction. In color, we have the total 12 tunnel in the city, in the old city. For the ground system, in the tunnel is implemented in 2 modes. We use a barred bar coupled conductor installed to 50 centimeters below the excavation level, or vertical ground roll. It's installed after its tunnel structure is completed. This is barred bar coupled conductor, and vertical ground rod is the intentional ground electrode. After we have the natural ground electrodes without, such as the reinforced steel bar, and we have another continuous isolation copper conductor into the smart tunnel. Because it is a problem of the smart tunnel in the city of L'Aquila, because in Italy we use the TT system. In the TT system, we don't have only the ground system of the medium voltage, low voltage substation, but we have also the private ground system of the private building. In the city with the high population, we have many ground systems with few distance between themselves. Main goal of ground system is protection of human life from electrical shock, prevent equipage management, reduce fire hazard and system failure, ensure stable electric operation. We have the ground system of building, private building, but we have also the ground system of the DSO substation, of the telecommunication, for example, the shield cable for the communication. Or we have also the ground system for lighting protection. This is a problem for the step voltage and touch voltage, but this is a problem, for example, for the galvanic corrosion of the water. We studied this problem with the ANSYS program, a FEM model, a finite element model. We started to study the simple model of ground system. For example, it's typical to study the hemispheric electrode, this ideal ground system, but not real. We can start to study the analytic formula. The analytic formula is this. This is a potential of the surface voltage. In this case, we have the resistance is a function to the resistivity of the soil and the radius of electricals of the ground system. This is a result of ANSYS model. We imposed, for example, the radius of the ground system of 1 meter and the radius of soil model of the earth model of 300 meters for have to the infinite potential to zero. And this is a result to analytic formula and to FEM simulation. We have an error of 1.2%, but this is an error make to the numerical model of the FEM is normal. And this is a potential in the different point of the surface of the street. After we study the vertical road, we try different formula in the paper, in the book. In this formula, usually we use the length of vertical road, we use the radius of vertical road, and we use the edge of the position of vertical road. In this case, we have the potential is possible to see with the polar coordination, and we have the result to FEM simulation, 39 ohm, respect to other equation of previous slide. We have, in this case, we have error to 2 to 8% to deviation to respect to FEM simulation. The formula is derived by the empiric model or the simplifying the model, the complexity model. In the last case, we used the buried copper conductor. In this case, we have a a wire, horizontal wire of 10 meters with the conductor 35 square millimeters, installed at 4.5 meters below ground. This is the formula tried to in the paper and in the book. This is more complex respect to the other, and this is the result. In the FM simulation, we have about 12 ohm. We have different value. For example, we have 8% of deviation, 14% of deviation. In this case, we have the 15% of deviation, but this is a problem of transcription of the paper respect to another paper for me. And in this case, the height deviation is due to the height depth installation, because this equation usually the method of the image, of the charge image and charge negative image. And we have a problem when the conductor is positioned in height depth. After, in the final test, we introduced the tunnel. We used the 10 meter long tunnel with the height of 3.5 meter and 2.1 meter, positioned to 0.5 meter below power ground level. And we have two ground systems, the ground system of the tunnel and the other ground system of the private building. In this case, we study the result of the ground system. We injected 100 ampere in the surface of the vertical row, and we have the result. We can see that nearly private road slightly raise local ground potential, potentially exposing nearby equipment to hazard voltage. The effect on the total earthing resistance is minimal. A greater buried depth of the vertical row reduces both touch and step voltage at the surface. The surface, the step of the surface is reduced respect to the case without the tunnel. In this case, we have the result using for a vertical row for private road and a barrier-coupled conductor for private for the smart tunnel. In this case, the smart tunnel create a shield around the tunnel and decrease the voltage step. And this is a result. In conclusion, we can reassume our study in 4 points. For realistic modeling, the FEM enables realistic modeling of a complex ground system scenario surpassing the simplification standard analytic method. This is a problem, the complexity of the model and the cost of the calculation cost. The suitable for smart tunnel, FEM is particularly well suited for smart tube application. The method was validated against analytic formulas for hemispherical horizontal electrode, confirming its accurating, and the approach of a robust framework to analyze ground behavior in environments with multiple interaction network. Thank you for your attention.
Thank you. Thank you, Mr. Fioravanti. One short question. We have time. Okay, I'll ask. Okay, please.
Allora,
In this case, the soil, we use different soil resistivity to 100 to 1000 of ohm meter. We use the radius of the soil of the 300 meter because it's because the resistance is calculated from the difference to voltage from the surface of the ground system where we introduce the current and the infinite surface, and the infinite shield, and divide the current. Is this installed at zero level. The other conductor is installed at 4.5 meter under the tunnel. No, there isn't. Yes, but we change the soil resistivity for dry to take the. Yes.
Okay, thank you. We'll pass to the next presenter, González Romero from Extremadura University, Badajoz, Spain. Please.
Okay, thank you very much, Professor. My name is Eva González from the University of Extremadura, and I'm presenting a two-stage optimization process for energy management and power allocation in a virtual power plant of residential microgrids. Well, this is the index, first the introduction, objectives, a brief description of the case study and the method, and finally the results and conclusions. Okay, nowadays we well know that there is a great increase in the presence of distributed energy resources in the power system, mainly because of the increase of renewable production technologies, and also there is a lower increase in energy storage system and also electric vehicles. So it poses a challenge in the power system, among others. One challenge is to integrate as much renewable energy as possible without causing congestion and instability in the power system. For this purpose, flexibility is needed, not only in transmission system, but also in distribution system. The flexibility is defined by the International Energy Agency as the ability to respond in a timely manner to variations in electricity supply and demand. In our current situation, residential prosumers are a primary source of renewable production, distributed energy production, but, however, the low power of both demand and generation limit their possibility to increase the business opportunity and also to support the grid. So we can use the aggregation to improve the situation. Two kinds of aggregation are considered in this paper. The virtual power plant, that is an aggregation and centrally management of distributed energy resources. These resources are not necessarily close together, and the main objective is usually to increase the relative weight to participate in electricity markets or include indeed in ancillary services. Another kind of aggregation is, we well know the microgrids. There is a local aggregation of resources, and as they must be suitable to be used both in connected and in isolated mode, their resources are more suitable to contribute to grid support. So the objective of this paper is to propose a two-stage optimization process to manage this kind of system. It's a virtual power plant that it's daily planned the energy of the resources of the entire virtual power plant are daily planned due to the energy management system, and it jointly manages several microgrids. Each of the microgrids contains renewable production, residential loads, energy storage system, and electric vehicles. And the objectives are economic optimization, but also provision of flexibility services and control of grid congestion. Well, this is the main contribution of the paper. I'm going to pass over. And this is our case study. This is a VPP that manages 2 microgrids, as this simple example. The microgrids are not connected to the same node of the distribution grid, but they are jointly managed by the VPP. These are the parameters of both microgrids in terms of power and limits and so on. And the electric vehicles are assumed to be available only during time slots during the day, during the first 8 hours in this example. This is the original data of the entire VPP. The entire VPP is, this is assumed to be forecasted values for both the generation, the photovoltaic generation, and also the demand of the entire VPP, the joint of the different microgrids. In this first situation, we have considered that the charge of the electric vehicles is performed at the beginning of the day at the maximum suitable power. Also, as we are going to perform an economic optimization, we need prices. We have used as a sample of prices the regulated prices for prosumers in the Spanish market in one specific day for the energy purchase and the energy sale. And also, we have assumed a local flexibility market. That is, in this case, in this example, we assume a band reservation as a flexibility asset, a power band reservation that is assumed to be paid at a constant price in this example. With this situation, without considering the energy storage system, neither the flexibility market, the electricity bill for the entire VPP is more or less 25 euros a day. So we are going to perform an optimization process in 2 stages. The first stage is the energy planning of the whole VPP. It's a daily planning, so 24 early energy values are obtained for both resources, energy storage system, and electric vehicles. The electric vehicles can work in both directions. They can charge or they can discharge. And in this first stage, the objective is economic. It's the maximum profit of the maximum savings. The second stage is starting for this daily scheduling for the entire VPP, we are going to obtain a power allocation for each resource of each microgrid. And it's only a 1-minute resolution. We are going to obtain only the next minute value for the power of both resources, energy storage system and vehicles. And we are going to include a technical objective, that is to minimize the power interchange between the microgrid, each microgrid, and the distribution grid. The method on the optimization methods are a genetic algorithm for the first stage and the nonlinear programming for the second stage. This is the objective function for the first stage. Basically, it'll try to minimize the money needed to buy energy, minus the energy obtained for selling energy, and the money obtained for the reservation band. And the variables of the problems are the energy of the energy storage system of vehicles and also the reservation band. The constraints are the usual, max-minimum power values, maximum and minimum state of charge value of both resources, but also a maximum difference between the beginning and the final day for the electric storage system to guarantee the available energy for the next day, and also the reservation band. And for the electric vehicle, we are going to impose that at the end of the availability time slot, they are fully charged. And for the whole VPP, we are going to add another constraint, that is that the maximum energy interchange with the grid is also constrained to a value to avoid grid congestion. In the second stage, the objective function is a technical target. We will try to minimize the power in this case, but it's only the next power value, interchange with the grid, with the same variables. In this case, we don't add the reservation band. And the constraints are the same than the beginning, but adapted to each microgrid. But also, we are going to impose that we are matching the planning for the entire VPP in both cases. And also, we are going to impose that the vehicles of both microgrids are simultaneously both charging or both discharging to avoid recirculating energy due to the lower efficiency. And this is the results. For the stage 1, we obtained that during the time slot the vehicles are available, they are smooth in charging in this case. And the demand is modified, the energy storage system is adapting for optimization. And the modified demand, that is considered the load and both the charging of storage system, is smoother than the beginning. As a result, we obtain a 29% savings in the electricity bill. Also, we can't guarantee that the grid congestion is obtained, and we obtain this reservation power band that is obviously is very dependent of the price we have considered, but it's quite high considering the maximum value of charging and discharging. In the stage 2, we obtain only one value for the next minute, but we have repeated the simulation several times to obtain the whole day. And in this case, we obtain this modified demand for both microgrids. We can prove that the power grid is constrained in the suitable band, and the reservation band is respected every morning. If we observe the state of charge of vehicles and energy storage systems, we can see that the vehicles alternate in charging, and at the end of the available period, they are fully charged. In the case of the energy storage system, one of them is fully charged at the beginning, maybe to provide demand decrease of the power reservation band, and the other one is changing. And as conclusions, we have achieved economical and technical optimizations. We have combined the planning of a whole VPP with the allocation of resources for the microgrids, and we have obtained energy economic savings, and we have fulfilled the constraints. Also, we have observed a cooperative behavior between the microgrids to meet the whole scheduling, and they have obtained economic benefits that wouldn't be possible in an individual operation. And finally, we have proved that the aggregations allows that low power resources can participate in flexibility markets, and the joint management of distribution energy resources can be energy and economic efficient. And that's all. Thank you for your attention.
Thank you, Ms. Gonzalez Romero. Please, questions. We have 2 minutes for the questions. One of our presenters leave time for questions. Okay. No questions? I have one question. What kind of tariffs exist in Spain? And if I looked on the calculations, but I couldn't find out that in which tariff you are focusing on this in the school, there was the tariffs.
Okay, thank you for your question. We have several kinds of tariffs, okay? For example, for residential prosumers, we had 2 options. That is regulated tariffs that are dynamically changing with market price. That is the one I have considered in this example. But you also can't have in a free market with a retailer, you can't have different tariffs, okay? For example, you can have a plain tariff for the selling or applying for buying or several combined, several dynamics and constant in different periods and so on. But it's an election for the prosumer.
It only differs from the time of the day, or also it depends on the regions of Spain?
No, it's for the whole Spain, it's the same value. It depends on the hour of the day, and it follows the energy market, the electricity market of the whole Spain. Well, sorry, the whole Iberian Peninsula. Okay.
Thank you.
Thank you.
Thank you very much.
Thank you. Next speech is Professor Antonio Gomez, please.
Okay, thank you, Mr. Chairman. Well, we are late, so it will take me probably only 5 to 7 minutes to present, because the idea I'm presenting here is very simple, straightforward. It's nothing very, very exotic. It's something like we wonder whether we can continue orienting PV panels directly to the south with the maximum energy production, inclination, and the like. So we are considering if there is a price cannibalization and there is a null prices in the midday, why shouldn't we focus panels to the west or to the east? That's the basic idea. So we are just presenting results of this idea, just to conclude that probably it's not a good idea to continue focusing to the south. So yeah, this is the solar paradox. You can see here the average hourly prices for the 24 hours here. You forget about 2022, because 2022 was a special year, Ukrainian war and the gas prices peaks and these kind of things. Forget about 2022. We can see here how prices have been decreasing since 2021. And now in 2024, we have basically very low prices in the midday, very close to those we had in 2016, 8 years ago. So the prices in relative terms have not increased, they have decreased, particularly in midday. So in fact, as I say here in yellow, in 2024, we had nearly 800 hours with null or negative prices in the wholesale day-ahead market. So I showed yesterday this slide, so I will skip. You can see here that a lot of hours, for instance, here this day, the week before the blackout, we have all the day null prices basically in Spain, in red here. So it's, investors are, being cautious about investing in new power plants, which are much needed to achieve the goals of the National Energy and Climate Plan in Spain. So the goals are risky in this moment. So, okay, this study is just to quantify what happens if we, instead of orienting the panel to the south to maximize energy production, we determine what is the orientation, the azimuth angle that maximizes revenue, annual revenue. So this is the idea. So the methodology is straightforward. We simply perform hourly simulations. We have all production. In this case, the result I'm going to show refer to Seville, the city where I come from, where the optimal tiled inclination angle is 34 degrees. Here will be much lower. So we use 8 years, the last 8 years, to the prices from the wholesale market, the same prices they have used before. So, and we test all possible azimuth angle from east to west, minus 30 to plus 30, in steps of 1 degree. So we don't need, for this purpose, we don't need any, any sophisticated any sophisticated optimization algorithm because there is a single variable, so we can simply perform the unexhaustive brute force search. So we compute the incomes for all from -30 to +30. That's all. So this is a very transparent way of doing that. There's no trick, no black boxes. It's very simple. So this is the same thing. So the only variable here is the azimuth angle for a fixed tiled angle and for the data of the prices in the wholesale market. So we compute the revenue and then compare what is the best angle. So as I said, we are testing Seville. I assume 1 megawatt of PV capacity. The tile angle is the maximum, the maximized energy. We have, the tile angle or the inclination angle is important for seasonal production. I mean, we have another work which is still under development, analyzing the tile angle, and the tile angle is also very important to avoid seasonal imbalances. But this is not the topic today. We are only focusing on azimuth angles. So, well, this is probably not very illustrative because there was a cloudy day. So, but in green you have the optimal 1 degree in Seville, in the south of Spain. The optimal azimuth maximizing the energy production is 1 degree. And then we compare -30 degrees, and we see that, of course, 1 degree provides more energy. But why do we want to have a lot of energy if the price is zero? So it's no need to do that. So this is and then this is the result of the optimization. Actually, the maximum income is for azimuth 8 degrees, whereas the maximum energy is 1 degree. So there is an 8 degrees difference between the maximum income or maximum revenues and maximum energy production. So this is the result for Seville. And for the prices of, in this case, 2024. These were for the prices in 2024. So we repeated this for all years in the last 8 years, and the results are different, as I will try to show here. For instance, you can see here from 2016 here to 2024, the optimal azimuth maximizing revenues. And we can see, for instance, that the first, from 2016 to 2019, there's an uncertain evolution. Why? Because in those years, in Spain, we had what we call the lost decade. We didn't install any PV capacity since 2008 to 2019. Until the new government modified the Royal Decree and the tax and this kind of, you may have heard in the news. So in Spain, there was a revolution starting in 2019. But so this year probably are not very representative. Anyway, we see here an increasing, and probably this is more correlated to, rather to the year, more correlated to PV capacity installed in Spain. And this is what we are trying to illustrate here. We illustrate here, you can see, as I said, this is in the horizontal axis, the capacity. This here is a mistake. This is gigawatts. In 2024, we have 32 gigawatts. In 2016, we only have 4.7 gigawatts. And the previous year, we have the same capacity. So these years are not representative. But so the other year, there's a clear trend to increase. And if we achieve the goals of the National Energy and Climate Plan, they consider that we will have 72 gigawatts of PV capacity, then the optimal angle providing maximum revenue would be 19 degrees to west. Why west and not east? Well, okay, because west in the evening prices are higher than in the morning for some reason. So probably, but amazingly, as you can see in the previous figure, in 2016, the optimal was looking to the east, not to the west. So it depends on the prices. So it's tricky because new storage capacity will modify the price pattern. So this is tricky. Anyway, so if we make a forecast in 2030, we should have the panels oriented to 19 degrees west. But they are now all of them oriented to south. I mean, to zero azimuth. And that's all. So the conclusion is that azimuth is no longer a fixed parameter, it's a strategic parameter, it's a strategic choice. So maximizing revenues is not the same as maximizing energy, considering also that the price of silicon are continually decreasing. and so you can install more silicon if needed. Shifting away from media production may capture higher prices. Okay, storage will change the panorama, but this is another story. Thank you very much.
Thank you. Thank you very much, Professor Antonio Gomez. You have questions? Okay.
Maybe a comment. I live in Belgium, so much more north. And my last panels were to northeast. Northeast. You say I'm silly? I'm not silly at all. There are several reasons for that. When it's sunny, panels produce about, without clouds, sunny without clouds, they produce about 5 to 7% of their peak power. Only that. Why? They are sensitive to red and infrared and not to the blue sky. So when putting a panel to the northeast, it happened to give power to function the toaster in the morning. So because it was oriented in the right way, because if you orient to south or even 18 degrees southwest, simply the sun shines at the back of the panels and you only have the blue sky. So in fact we should not have one single angle, but having a split angle. So apart to the northeast, that's extreme, but at least to the east and the west.
Yeah, actually, this is a modest work on analyzing only the azimuth in case of the, to maximize the income, the revenues. But you are right. I mean, there are so many factors: the albedo effect, bifacial panels, the shadows of trees in the morning. I have a plant, so as I said yesterday, so I'm suffering some shade from the trees of my neighbor in the morning. So what you say makes sense. So ideally, we should have angles that could be modified on the fly. I mean, every month or something. But this is, it's very expensive.
But let's say that. When it's cloudy, they anyhow work in any direction. So you can save on your converter and having not more converter because you know that they are not at the middle of the day. So if you look at converter saving in price, because you have to renew them almost 3 times for one life of the panels. So even that you could consider.
Yeah. Anyway. Thank you. The situation in Belgium is quite different from Spain anyway. So we have the problem of temperature. In summer now, for instance, at home, I'm producing much less than in April, in June and July, because of the temperature of the panels. So my panels are producing maximum in April. Anyway, so thank you.
We have the best panels in Spain. Thank you, audience. Thank you, all the participants, all the presenters. And I think that everyone is hungry. Welcome to the lunch. Bye-bye.
So good afternoon, everyone. My name is Ernesto Pereda, and I will be the chairman of this plenary session number 3. And it is my pleasure and my honor to introduce you briefly our plenary speaker, Dr. Tariq Masood. He's assistant professor at Frostburg State University in Maryland, United States. He also holds a PhD from the University of Bath and a master in philosophy. He's a member of the Royal Engineer Council in the UK, a senior member of YEEE USA, among other memberships to prestigious engineer societies. And he has also a large trajectory, both professional and academic. And he will be talking to us about sustainable smart grid technology option to resolve operation and control challenges of electrical power system. Please, Professor Masood, the floor is yours.
Hello, okay. Thank you very much, sir, for a wonderful introduction. My question to audience, why we need a smart technology, smart grid, smart approach, why we need a smartness? Everybody talk about smart. What is smartness? And why I'm here today? To understand what is behind the smart. Anybody? It's a big word, a business word. Everyone wants to become smart. What is the phenomena behind the smartness? Okay, another question. I have produced a 400 megawatt power in Madrid. I want to transmit from Madrid to here is Tenerife. How much power I can receive over here? It would be the same 400 megawatt or it will be less? What type of parameter you need to control? What is that? We have losses. Okay, anybody else? Why we have the losses? What is it? Anybody else? So, no, another question. When we transmit our power, interestingly, I have a chemical background and I have electrical background as well. My slide you have seen the chemical. Today, purely you will see me, today I'm electrical engineer. Okay, my another questions. When you transmit a power or fluid, or when you move in the line, you are facing some forces. Okay, what is force called? We have a different type of materials, like we use stainless steel or some other materials, and it has different resistivity. Then we have platinum, gold, silver, etc. What is the main principle or differentiate of each material? What is the fundamental approach to understand which is the best material? Which one the top one? Surprisingly. Okay, so you have the line. This gentleman told me there is power losses in the transmission line. Which is the force which is restricting, the force which is losing or consuming a power? What is this called? Now you have 3 types of material. One is a platinum, gold, or silver. Which is the most precious metal? Is a platinum, gold, or silver? Which one is that? The top one is the platinum, which is expensive. So if you transmit a power in the platinum material, you have a minimum impedance, line impedance. Impedance, technically, it's a resistance. Okay, so then you can use the other form of the material is a gold, then silver, then stainless steel. These are the different material which have a different impedance which resist the power to flow. Okay, so question is that these resistance, is it possible you as an engineer control or manipulate the resistance to become a smart, to become a more efficient? Smart phenomenally mean more efficient at minimum losses. Or would say, in the maintenance terms, we use a CM and PM. It's a corrective maintenance, and the CM corrective maintenance and PM preventive maintenance. Why we do corrective preventive maintenance? To achieve 99.9% reliability to run system at maximum operational reliability. So question is that when you run this system to become a more smart, means the system has a 99.9% efficient, but it's difficult to achieve that. Okay, you need to pay, you need to consume a lot of resources to stand at 99.9%. That's not an easy job to become a more smart, more efficient at minimum cost. That's not possible. Now today I'm here to demonstrate to you how I can become a more efficient, more effective. If I need to transmit power of 400 megawatt from Madrid to over here at minimum losses. It's not possible. It's ideal. Ideal, we cannot become ideal. Mean 400, you will receive 400. It's not ideal words. So, at minimum, we have different form of the power losses to become a more efficient generation, transmission, and distribution. Each area has a different power loss and power consumptions. So, today we'll talk about bigger. I have 35 minutes. I don't want to take more time. So, just will demonstrate you effectively. So these are some technology options which I talk about today. So if I can see here, so that is the area which we have electricity requirement, civilization, we each areas. Okay, now this is the moment if the electrical power outages happen. Okay, over here, so now this is the first area which I talk about, the generation, step up, step down generation, and loads here. Okay, that's a poor, complete power architecture. Over here, now, this is the very important slide. My question is that if I can see in the generation side, I have a 65% losses, and transmission distribution 7%, and over here it's 88%. Now, my question is that as an engineers, can we reduce these losses, become smart being efficient, reduce the losses? Can over here, we can bring less than 2 or 3%, become more efficient, and over here as well. Now, anybody aware of that power generation section? Have you any mechanical guy over here? The generation side, who power turbine, who know the power turbines, gas turbines, steam turbines, operations? Did you know the steam turbine, the power generation, how much efficient? How much performance we can witness from the steam turbine or gas turbine? No. Anybody else? Yeah. Anybody? So, yeah, gas turbine. So remember, steam turbine and gas turbine both have a same principle for the operation. So there is an inlet guide vanes, IGV, stationary blade, rotary blade, then it will generate the power. The steam turbine and gas turbine, there is a stationary blade and a rotary blade. There is a space between stationary blade and rotary blade. Did you know how much space in between both blades? Is 6 millimeter. It's called the cold space. When the temperature reaches 400 degrees Celsius, did you know how much is space? No space. It's called the hot space. Now, this is the space where we have 65% unconverted energy pass-through will go to the exhaust. We use a combined cycle, bring back to convert maximum. But the question is that the steam turbine, gas turbine give you maximum 35% performance. That's it. So this is the area which we need to work. Is it possible? At this stage, it's not possible. If you reduce the space, then these both blades will kiss or touch to each other and they will damage. That's not possible. They have a different form of thermodynamics. Now, this area need a more improvement. Then second is a 7 to, that is normally, in my country where I came, I'm from Pakistan where we have 30 to 40%, but I'm residing in the United States. So this area is an area which we have a huge number of technologies which can help to bring the losses less than 2%. And then this is the consumption, they are a different area. Now, what is a smart basically? Smart grid does not just mean smart metering. What demonstrate smart grid mean? Technology, modernization, transmission system include wires, substation, transfer switches, and much more. Quality, efficiency, power network, and energy use. So if you can see, smart does not mean just a smart. You need to demonstrate here the modernization, transmission, substation, transformer, certainly reliability, quality. Anybody have an industrial experience? Have they worked in the industry? Interestingly, I run my both profession parallel. I worked 25 years in petroleum industry, and 25 years I've been teaching in Texas A&M University in Qatar campus. So both parallel. So why I ask you, industry, the reliability in industry is very, very important. Why reliability is very important? No one wants to trip their pump. No one wants to trip their gas turbine. No one wants to trip their engine or compressor or turbine, etc. What is the reason? If your compressor trips, if your pump trips, so it will lead to trip whole system. 1 minute costs you $1 million. So in order to achieve 99.9% reliability, they installed a standby system. If one pump has some technical issue, something happened, the second pump will come on operational and keep the system running. Some area to keeping a standby is expensive if the pump is tripped. So then they have do a different models, dynamic model to demonstrate which is more technically and economically reliable. They adopt the quality. So the reliability in the industrial spectrum is very, very important to achieve 99.9 in order to keep maximum uptime, zero downtime. The people will be happy, you will get the promotion, you will get the bonus. If there is no trip happen last 3 and 4, 6 months. We have a even break-even point. In after 3 years, how much production they have achieved? Did anything happen? No. They will get a bonus, they will get the benefits. So that's want to keep reliability motivated and keep it up on the brink. So that is the reliability, efficiency, and network energy use. Of course, when the system is reliable, certainly it's efficient. If it's not reliable, certainly it's not efficient, it's not smart. Okay, now, in a power system, so the entire energy conversion obtain a smart infrastructures. The first, decentralize the energy system. Number one, communication solutions, smart substation, automation, condition monitoring, distribution automation, building automation, smart metering, and the overhead power transmission system. So these are different sectors. Every year I will come. Today I will cover power transmission system. Next year I will cover maybe decentralize some of the sector. Next 5 and 6 years you have to attend my lectures, and every year I will demonstrate you each section, the smartness or the smart grid spectrum. Okay, so today we'll talk about only power transmission system. Okay, so smart technology ideas and concept. Definitely smart, bidirectional or power flow. Both happens, the improved reliability, security, efficiency, and the last one is consumer level. What is the consumer level? Why they want to be a more effective consumer? Who are the consumers? You are the consumers. Why we need to educate the consumer? What's the objective behind the consumer? Why we need to educate the consumers? Okay, okay. How they can be they can use the energy more efficient way? Mm-hmm. Mm-hmm. Exactly, exactly. So if you see there is some electricity bill, they will brief you about the peak time, off-peak time, peak time. So they will shift your load when is the off-peak and peak time. Accordingly, they will educate the consumer. You will, if there is an off-peak, so you will get less rates. If peak time, it will be expensive. Some activities you will go on the off-peak in order to save some and more efficient. They will give you benefit. They will give you dividend if you change. So that is the purpose, to educate the people in order to, you have everything efficient. If you did not switch off your air conditioner when you left your home, if you did not switch off your heating system when you left your home, so the energy is not efficient. So that's why they want to consumer to be educated. If you are not at home, you should switch off your air conditioning system, or you should switch off your heating system as well. Okay, now what is the great influence on the smartness? The first here, over here, the external influences, operational factors, grid condition and requirement. That is a major factor, how we can demonstrate over here. The first is the variable power supply. How many people know about the variable power supply? What is the variable power supply? Variable power supply, from where it comes from? Renewable, excellent. So which is not consistent, that is called the variable power supply. That is the first inference, that is the grid condition. The second, integration of distribution resources. Distributed resources mean you have multiple variable supply and link with conventional and non-conventional power sources to integrate to each other. What do you mean integrations? Integration mean if something happened with the renewable energy resources, so the conventional system will come, it's called the cascaded loop control. When something happened or weather condition change on the renewable energy resources, so immediately the conventional power system will come in operation and take the load in order to overcome or to trip the system or any contingency plan. So it will come immediately. Increased distribution between resources and load. That is the first condition here. Second, operational factor, greater transmission network complexity. Sometimes the network is very complex, very integrated. Second, aging infrastructure, lack of expert, high power quality delivery. Can I ask the question, why, what happened? Why aging factor is influencing the power system operation? What is the factor in the aging factor? If your transmission line is too old, what will the impact on the power system? Yeah. Only one word. When, with the passage of time, what could happen with the material? You have enforced material, stainless steel, silver, enforced material. With the passage of time, what could happen with the material? Yesterday, somebody asking me, I was walking and they said, don't tell me why. I told him, I'm getting old. What has happened? What is this? With the passage of time, the material starts deteriorating. So when the material starts deteriorating, so the quantum of the material will create a huge amount of impedance. If your losses of new line is 2% or 3%, after passage of time of 10 or 15 years, maybe this line will lead to a losses maybe 7 to 8%. The reason? The deterioration quantum of the material. So this material causing to a huge effect of the in force that is ultimately consuming a real reactive power. So that's the first aging factors. So we, in order to address this factor, we have the technology to solve the aging factor. Instead of installing, stretching new infrastructure, stretching new lines, we will install a more reliable, more efficient technology to overcome aging factor. So the next is the high power delivery quality, of course. Then the last one, very important, legal and regulatory framework. What is a legal and regulatory framework? Did anybody know? The grid codes of European Union or Spain, do you have the legal framework? Yeah, so the legal frameworks, you have to maintain a certain level of voltage, no dip, no oscillation, number one. To maintain certain level of frequency, 0.2, 0.2, acceptable, not, otherwise you have to pay the plenty. If your oscillation is varying, you have to pay the plenty. So the last year, integration of renewable resources and CO2 reduction. How many people know about the CO2 reduction? And how many people know about the CO2 reduction? What is CO2 basically comes from? Did you know when we get a fuel, the gas fuel, that is methane gas. Methane gas contain hydrogen sulfide. Anybody know H2S? This is hydrogen sulfide. The hydrogen sulfide is a form of mercaptan. That is, mercaptan is a permanent connected the chain of organic components. The free H2S you can remove. You can use a different sweetening unit, remove the hydrogen sulfide. Hydrogen sulfide is a permanent component coming from the reservoir when we extracting oil or gas from the reservoir. Hydrogen sulfide is permanent components and carbon dioxide as well. So the hydrogen sulfide is a hazardous material. It's connect with nitrogen, it's connect with oxygen, so it become a NOx and SOx. That is most dangerous gases. It's called the greenhouse gases, NOx, SOx, and carbon dioxide certainly is there. Carbon monoxide, if it's incomplete, so you will also find carbon monoxide. But if it's a complete combustion, you will find carbon dioxide. But NOx and SOx comes from hydrogen sulfide. Okay, so question is that my fuel is a sweet. From where NOx and SOx came? Yes, but mercaptan contains still with the chain. You cannot break mercaptan unless you need to use different form of catalyst. Okay, so that is CO2, greenhouse gases. Energy efficiency, of course, to be become. In order to address these all issues, anybody raise the hand how we can address these all issues in one go? What you need to do? Complex structure, which you talked about in the last slides, for smart solutions to address these issues, all of them. How we can address? Next slide here. First thing is called the self-healing. What do you mean by self-healing? If you are sick, you will go to doctor, or you will take the Tylenol or Panadol, something, and it's okay. What do you have to do? You need to go to doctor, or just go to Google and I am sick, tell me which medicine I should use it. What is the meaning of self-healing? The self-healing, the system must be efficient, smart enough to detect, analyze, and immediately take the action. That is called the, what is recently in war happened now in Israel and Iran, that they have some missile system, they will detect and activate immediately what had happened. That is a different story. So the system is called the self-healing. You will observe the dangerous boundary, you will observe the operational scenario, and take immediately action. That is called the self-healing. The system should, enough support, they should not wait, operator will come, press the button. No, the system should have enough capacity and capability. Maybe in future AI system will take place. Everything will be self-healing. So it will detect and immediately respond. Next is empower incorporate consumer, ability to incorporate consumer, behavior, design, operation, and last over here, tolerant to the cyber attack. That is important here. The grid mitigate the physical and cyber attack, provide power quality 21st century based on the CBM, accommodate wide supply demand, a grid accommodate resources, fully enable supporting by the competitive market. In 30, 40 years back, when I make a telephone call, I need to pay 1 minute, I think $2 or $3. There is no other competitor in the market. No, the telephone call is free. So, when you have multiple generations, multiple distributor, multiple transmission in the market, so efficiency, the effectiveness go high, and the cost will go down. That is competitive purpose of the competitive market. Okay. The next is extension internet connections, increase power exchange, transmission large work, long distance, renewable energy resources to be located where it should be connected. Okay, this is one example here. If there is something happen, it's a complexity that are major blackouts, just I have talked about. So if the system is not responding timely, like self-healing or the education system, so what could happen in August 2003 in the United States was completely blackout, and February 2008 is as well. What is happening basically here? How many people know about the compensation factor in the power system? Why we need a compensations? When you transmit a power from Madrid to here, so to deliver a power, you need to balance to transmit a power, real and reactive power. So you need to maintain a certain level of reactive power with real power. Now, question is that to compensate, we use a 3 different level of compensations. What is the first level of compensation? In case if your voltage drop, to boost the voltage, what do you need to do? What do you need to do if your voltage drop? To boost the voltage, what we use? Which device you will use to boost the voltage? He mentioned transformer. That's fine. Anybody else? Yeah. So remember, we need a reactive power. Whenever for example, I want to maintain a 400 kV voltage. If my voltage 390 or 395 voltage drop, I am engaged the grid codes, grid law, they want to maintain every time 400, then I need capacitors, compensation, that is reactive power compensator. If my voltage gone 400 to 5, again I'm engaged grid codes, I need to maintain a 400, then I use the inductor. They will absorb the reactive power. Okay, over here what has happened? That time they used the reactive compensation by generation 2 technology. Generation 1 technology is a conventional way to use CB, circuit breaker, CB based compensations. What CB do? CB open or close. When the compensation need, circuit breaker will close and compensate. If they need to remove, it will open. So it's called the CB base. Did you know CB base compensator, how much time it will take? 120 to 180 milliseconds to open and close. In generation 2 compensator, they need 2 to 3 cycles to compensate. 2 to 3 cycles mean 40 to 60 milliseconds. They use G2 generations. Now, in the one cycle, sensorial way, taking only one cycle. If the compensation did not happen within a one cycle, then trip will happen. So over here, they use a G1 compensation factors. So because of G1 compensation, there is a mechanical oscillation happen, and there is a blackout hold United States. Today, they have installed a G3 compensation as well. This is taking one cycle only, which I talked about today. Okay, now, if you can see here, very important slide here. This is my capacitor and inductor. So that is a complete story. Inductor and capacitor is a complete story how the power system operation is performing. So the first here, the power flow issue, stability issue, or reactive power management is complete interfering the system, how the system is performing, and we need to balance the capacitor and inductor here. Okay, next come over here. This is my most favorite slide. If you can see here, this is my different transmission line here, and 1, 2, 1, 3, 3, 4, and 4, 5. My question to you peoples, this line is loaded 60%, 40%, 30% at different loaded. You are working on one transmission line, as a transmission engineer. Will your company will allow you to run this transmission line only 40%? Will allow you to keep your transmission line 40% load or 30%, 60%? Will you allow you to keep 60% load? No, your company is paying to the corporation that I have borrowed or I have rented this transmission line. I will 1 year rented or 2 year rented, I will pay you the money. No, your engineers, if you are not loading transmission line at its maximum level, maximum capacity, what could happen? What could happen? Your company will not allow you. They will sack you. They are going to pay. You have allowed to maximum transmission power, but if you are unable to load your transmission line of more than 70 to 80%, your company will not allow you to work with them because you are an engineer, you must load a maximum to get maximum benefit out of that. Then what your company is paying? They are paying capacity payment. So the capacity payment, you have agreed, if I load 80%, this much money you will charge me. No, this is your responsibility. You pay 30%, 40, 20, you have to pay for that. So none of the company will allow you to pay the capacity payment. You have to load the transmission line at maximum to get maximum value from the network. So the question is that when it's not loading, it's mean you have not a proper technology to load the transmission line. Could be the reason loop flow, bottleneck, loop flow, or transfer capacity. These could be a 3 issue. If I'll come, sorry sir, I cannot load because of loop flow. Oh, 5 minutes? Okay, so then you have, after a few slides, I will go to the right slide and then we will wind up. So then you have to load, by using the technology, you have to load the transmission line at maximum capacity. Okay. Now, what is happening basically? What is the capacitive and inductive just we talked about? It's called the electromagnetic and electrostatic behavior. When you develop electrostatic behavior, so you will allow to reduce the line impedance. What you are doing? To reduce the line impedance, that is natural phenomena of the material. When you create electromagnetic field, you increase the impedance. Okay, so that is vice versa. Now, next here. So the first year, this is important. The first, if your capacitor is more here, inductive is less, it's mean the over voltage. Mean you have a more capacitive, the line could be over voltage, 400, 410, 420. Now, if you have equal, capacitor and inductive have equal, it's mean system is not loaded properly. It's mean system is like this. So if the capacitor and inductive equal, system is not loaded. So, no, over here. Inductive and capacitive, less. Now, I have explained you three conditions. I'm not allowing you operate here, I'm not allowing you operate here, I'm not allowing you operate here, then where you want to run the system? If capacitor is less, inductor is low, not allowed. If equal, not allowed. If inductor is more, capacitor is less, not allowed. Which condition I need to run the system? Quickly, please. There is any fourth condition? Quickly. Professor told me only 4 minutes. Quickly. There is any fourth condition? Fourth condition? You are over here in the smart room. You are listening smart grade lecture and you must be smart enough to answer my question. There is any fourth condition. I'm not accepting capacitor inductive, higher and low. I'm not expecting equal. I'm here. Which one is smart approach? What's the fourth condition? Is it any fourth condition? Can you raise the hand? There is any fourth condition? Fourth condition? No, I'm talking not DC. I am here AC talking about. So because 3 minutes I cannot go this side. Okay, there is a fourth condition, I will show you. This is the fourth condition. What do you mean this condition? What do you mean this condition? The system should switch on and switch off within 1 cycle or 2 cycles. That's the fourth condition. Okay, how it's happened? So here you can load transmission line up to 90 or 80%. Okay, this is my last slide. Give me a few minutes for this one. Okay, now listen carefully. This is my both network here. And I have connected without STATCOM. STATCOM is my smart device who provide me capacitive and inductive behavior, positive and negative, both sides. Okay, I switched off my STATCOM. When I change the load condition in scenario 1 here, A load, and you can see my voltage dropped here. In condition 2 light load, my voltage increased here. In condition 3, when line 1 dropped, my C condition, the voltage dropped. Load rejected, voltage increased. Okay. If you see here, there is a voltage oscillations happen because of your grade condition operation, because of you change the scenario. Now, when I installed a smart device, that is my STATCOM here, when I commission STATCOM, can you see here? Straight line. What's happening? This gentleman is playing with that. So it compensates your inductive and capacitive within a cycle. So within a cycle mean, my generation 1 compensations 120 to 180 millisecond. My generation 2 is a 1 to 2 cycle. And my STATCOM is a generation of 3 smart device who compensate in 1 cycle. So that's why you cannot observe when this gentleman is playing with, juggling with the conductor and capacitor behavior within a cycle. Thank you very much, sir. I hope you enjoy.
I'm sorry I have to cut short such an interesting talk. It's very relevant. We were also talking that something that happened into our mainland system in Spain is possibly related to this kind of effects in the network. So I guess there should be some questions in the audience for Professor. Yeah, indeed, very much. Sorry that we couldn't make it longer. Any questions? Comments? No? Yeah, there is a question there in the audience. Yeah, moment.
Thank you for the interesting lecture. I have a question related to the first part, when you made the comparison of a smart system being very efficient. And I'm curious to know your opinion in the energy market. Who is interested in having an efficient system? I can't see any player wanting a lower energy demand. I see the importance of an efficient system, but if I'm producing energy, I don't want people to consume less, I want people to consume more. If I'm paid to transport electricity, I want, higher demand. What's your opinion on who has an interest, who has a stake in making the system more efficient?
Thank you. DOE, Department of Energy in the United States, they are investing $1 billion. And interesting, I am the part of, there is one Senate committee who's vetting a different research proposal as well. So technically, they want to become more efficient. The system should operate. No, we have seen a lot of proposal coming based on AI, artificial intelligence, they're linking up. See, there is every time room for the improvement. I mean, if your glass is full of water, there is a room for the improvement. Still you can improve. So there is a most spectrum, in particular the wind, solar, and geothermal is a huge potential in the United States. Geothermal in Oregon State, I've been in Oregon State University as well, huge potential. And I have, interestingly, I have worked in the well performance and geothermal as well. So we have also developed a lot of model in the geothermal. So the efficiency is every time at the top spectrum. We also use the best practices. Best practices mean you should drive maximum value at minimum cost and minimum losses. That's happening. Thank you very much.
Thank you very much. Any more comment, questions from the audience? No? Yeah, of course. Or you can go there and I will take a picture. Huh? I think it's easier. Let me check. In the meantime, thank you very much again, Professor Mashut, for the very, very nice talk. Please. Come here for the picture, please. Thank you very much. Don't be shy. So you can go outside.
To introduce me, my name is Pilar Suarez from University of Extremadura, Spain, and it's a great honor to me to conduce this session. We have 6 posters at first. Each presenter has 5 minutes for their intervention, and then we have 2 minutes for possible questions. So I'd like to give the floor to the first speaker, ICREPQ, from USA, poster number 241.
Thank you. Can you guys hear me? Can you guys hear me?
Yes, nice and clear.
Oh, thank you.
Yes.
Yes, it is possible. Okay. Yes. So I would be presenting on a topic called achieving AC power flow convergence through generator active power redispatch. Now, AC power flow is very common. We all know what AC power flow is, and it's one of the most fundamental analysis you can do in power systems. However, achieving convergence or getting a power flow case to solve in large systems can be quite difficult. Now, different factors, for instance, the initial conditions affect the solution. The solutions to the power, or if you have an initial voltage magnitude and angle that is far from the actual solution, your power flow case might not converge. Then another issue could be the dispatch. Having a bad cause a power flow case to diverge. So in this paper, we are addressing power flow convergence issues, looking at how the generator and load dispatches that are causing the power flow case to diverge. And then when we identify these critical transmission lines, we then redispatch the existing generators to ensure that the power flowing on those critical transmission lines are below their rated values. So this is the strategy that we're using to flow for large systems. Algorithm here, bus mismatch. Now, DC power flow would always solve true in AC power flow, but we can use the information from the DC power flow to help us in achieving convergence. So we get this solved DC power flow of this power flow model, and then we look at the lines connected to this critical bus. Let's call it bus K. Then we look at, are there overloaded transmission lines in this bus? If there are overloaded transmission lines, we look for the line with the largest overload. And once we get that, we can call that our critical critical transmission line. So that's the first to alleviate. Now to the injection shift factor, distribution factor, PTDF. Now this injection shift factors basically tells us the generator
Samuel, please,
to
you
this
have
critical transmission
Samuel?
line. And essentially we get the bus with the largest factor. Yeah, can you hear me? Yes, can you hear? I can hear you. Can you hear me? Can you hear me? Hello, can you hear me?
Samuel, you have a bad connection.
Can you hear
we
me?
have problem with your connection. You have finished your explanation, please.
Yes.
Okay, thank you.
Oh, sorry. Yeah, I'm on. Okay. Sorry, can you guys hear me now?
Thank you, Samuel. Sorry for the problems. Thank you. We have to pass to next speaker, Samuel.
All right, then, no problem.
Thank you for your presentation.
It's fair. It's cool.
Well, next speaker is Pilau from Portugal, poster 265.
Yes. Yes, I'm here. Okay, I'm going to try to share my presentation. Where it is. Hello. I can find it. Where is it? I'm sorry. I'm trying to.
You have a icon in the bottom of your screen?
Yes, because I can't have my presentation in the. I can't find it. Why? I think I have also problems with the internet because I'm listening in delay my voice.
You must have to
share the screen. I don't know why.
You must have different options to share your screen.
Yes,
all screen or document, maybe. You can share the huge screen or document or presentation, only presentation, maybe.
Share screen, okay, but
we try a minute, and if not,
my God, I don't know why I can't find my presentation here.
Rosa, we can follow the next speaker, and then at the end of the session, we try to connect again with you.
Okay, sorry.
Okay.
But the connection is not very good because I'm listening my voice in delay.
But it's a problem with the shared. Well, you try to connect with you at the end of the session, okay? Well, then next speaker is Bokoni from Hungary, poster number 278.
Hello, can you hear me?
Yes.
Okay, then. I tried to keep the network connection as low as possible and only share the poster presentation. Can you see the poster as well?
No, just your screen. Tartia a presentas, but not the poster, not the document, not the file.
Okay. I see the poster already.
We are seeing your monitor, but not your presentation.
Strange. Now?
Yes.
Yes, yes.
Right now.
Great, already works. So, hello everyone, my name is István Vukin and I would like to give you a short overview regarding our research. The research title was about how to implement the sustainability into the energy sector, so powering sustainability, comparing the ESG strategies of Hungary's leading energy companies. As far as you know, that the sustainability is not only a buzzword anymore, but it has much more higher influence in the international energy companies and governance bodies and everywhere else, and not only just administrative task and duty, but this is already built into the company strategy itself, and it has influence on the geographical, technical and economic aspects altogether. So therefore we decided to have to involve the four major energy companies in Hungary called E.ON, MVM, MOL and Opus Global, and analyzing their motivation, do a comparison analysis regarding different approaches and strategies, and somehow to work out a measuring possibility which approach is more effective and leads to the targets what is defined not only on company but on national level as well, based on the EU regulation, of course. So the two major activity what has to be stressed out is the ESG, the environmental, social, and governance strategy, and the other one, the CSR, these activities coming from the Green Deal EU regulation. And both of them force the large companies to put together their own strategy, KPIs, and on an iterative way from year to year, make the analysis and do a transparent documentation regarding the results. So the key for ESG focus areas were different at the four companies. So first of all, you can see at E.ON Hungary, the grid modernization and renewable integration was the focus. On MVM, the green transition strategy, so much more high level and EU regulation wise. At MOL Group, a pragmatic sustainability approach, because they are basically an oil and gas company, but they have to deal somehow with their target vision and strategy this area. And Opus Global is a rapidly developing company, and therefore they are utilizing a very updated ESG framework to fulfill the requirements, not only on power and gas infrastructure, but on the renewable energy implementation as well. So analyzing the documents, we decided to make interviews with all the company representatives, and based on those questionnaires and the strategy documents, we made the comparison analysis on different aspects. So as you can see in the table, the aspects were the renewable integration approach, the emission reduction strategy, the innovation focus, and how is it built into the business strategy at the company, and the governance and reporting activities, and is it an ad hoc or a planned strategy-wise solution. And as a conclusion and insight, I would like to stress out some sayings based on the information and our research. So first of all, integrating the ESG metrics into a BSC, a balanced scorecard framework, enables the companies to the systematic alignment of sustainability objectives. We worked out a balanced scorecard structure framework, and it seems to be a very effective decision supporting tool to them. The second thing, the innovation and digitalization are quite good technical tool sets to enable the ESG targets and visions. Anyhow, the supporting processes and the integration of the renewables and the operational efficiency are the key factors and elements of the whole monitoring prospect. Third, the KPI-based approach is a really difficult approach from one side to fulfill all the needed information, but on the other side, the data-driven decision making is the most transparent and objective approach to keep and plan the next steps in a midterm or long-term planning period as well. And last but not least, the ESG embedding into the financial planning through scenarios and risk quantification can be a capital allocation process to have not a maximized business value, but a sustainable business value on the long run, to take into consideration the climate policy goals. And it was really, really nice to see that this is not a science fiction, but already possible solution on market operated companies as well. So that's all from my side in a nutshell, and I'm still open for any question or comment. Thank you.
Okay, thank you. Some question, any question or comment in the presential room or virtual room? Then I have a question. Are the Hungarian government funds available for photovoltaic project, energy project?
Yes, there are many. And there was a rapid change in the last couple of years, because until 2020, the share was not more than 50% in the whole energy mix. And the incentives results some breakthrough in 2022 and 2023, and currently I guess we are the leaders regarding the percentage share of the total built-in energy mix, and therefore the government decided end of last year to change the incentives, because it can be a reasonable decision on pure market wise already. So the incentives get and targeted the aims, and right now the continuous operation and the stability of the network is the new number one priority. And therefore since end of last year and this year, many battery storage systems at least projects opened. The implementation are still ongoing, but that will be the next step.
Okay, thank you. Thank you very much. So I'd like to hand it over to Rubio Clemente from Colombia, poster number 304.
Hello. Can you hear me? Hello. Hello.
Yes, yes.
Yes.
Go ahead.
Okay.
Yes.
Okay, thank you very much. So I'm going to, are you seeing my screen, the poster? Yeah. Because
yes, it's
if
okay.
I
It's
present,
okay.
okay, thank you very much. So good afternoon, everybody. My name is Ainhoa Rubio Clemente. I'm going to share with you this work titled Environmental Impact Evaluation of an Oscillating Water Column. As you know, renewable energy technologies are critical for reducing the reliance on fossil fuels and mitigating the environmental footprint of energy production. Among this technology, the oscillating water column is a promising alternative for harnessing wave energy. However, in order to secure its suitability and sustainability, it is important to assess the environmental impacts. And for this purpose, we can use CONESA's methodology to evaluate these environmental impacts throughout the different stages, such as from the design and manufacture of this technology until its operation, maintenance, and also disassembly stages. So I'm going to meet here. So for this purpose, we use CONESA's methodology, and there are different stages to be followed. First of all, we have to identify the activities susceptible or to generate environmental impacts by every stage. And then we have to identify the environmental factors susceptible to receiving impacts, such as, for example, the physical, abiotic or biotic, and also the socio-economic factors. And then we have to identify every component, for example, the landscape, the air, the water, the wildlife, and so on. And then after that, we have to identify the environmental aspects. During the fifth phase stage, we have to identify this environmental impact, and then we have to assess them. To assess this environmental impact, we can use this criteria, the intensity, extent, movement, persistence, reversibility, synergy, accumulation, effect, periodicity, recoverability, and so on. And then these criteria are included in this mathematical formula to know the significance of each environmental impact that has been identified. After that, in the seventh stage, we have to define those preventive mitigation and also compensation measure through our environmental management plan. So as results, in considering those stages, we have here, so I'm going to, sorry. Okay. So here we have several tables where those components and factors, components and activities, and also environmental impacts are listed during the design and manufacture stage, also during the operation stage, and so on. And we can, as results, as findings, we have that the operation of oscillating water column results to have moderate and also severe impact on the socioeconomic factor, particularly due to the effects these technologies can have on tourism and also fishing and job creation. This is a positive impact. And also the quality of life and the acceptance of this technology by the communities there in the area. During the maintenance of an oscillating water column, impacts in water can emerge due to the spillage of oils, for example, which led to the deterioration of the water quality and also the air quality. During the decommissioning phase, communities may face impacts due to the inaccessibility to energy service. However, if this stage is well designed, plans can increase the application of this type of technology. Additionally, it is important to know that mitigation strategies should be considered during all the phases, during all the stages, even the design stage, to allow the maximization of these benefits of this kind of technology, while reducing the potential negative environmental impact. And finally, as conclusions, we have to say that the installation, operation, and maintenance of an oscillating water column generate moderate environmental and socioeconomic impact. Some of them are negative or have negative effects, such as, for example, soil, water, and air pollution, and even noise during several stages, particularly during the operation of this technology. And also, it can cause the marine fauna alteration. However, there are several benefits that are standing out also, such as, for example, the increase of the quality of life of the communities, and also the creation of jobs, of new jobs. And it is important to know that to ensure the suitability and also the sustainability of this technology, mitigation strategies should be implemented, should be taken. And well, I think it is important to know also, and to end, to concrete these environmental impacts, negative or positive, either negative or positive impacts regarding the specific area, because it is not the same to implement this kind of technology in a conservation area or offshore or onshore. I think for me it's all. Thank you very much.
Okay, thank you. Any question, comments? Well, Ainhoa, Do you think your results are generalizable to other coastal areas outside of Colombia?
No, it can be generalized because every coastal zones are different. For example, in Colombia, there is one of the countries more biodiversity worldwide. It is not the same in other countries, for example.
Okay, thank you. Well,
Thank
we
you.
have to next speaker. Alan Calderon, please, from Germany, Peru, the group of researchers. Poster number 311.
Hello. Is possible to hear me, please? Hello. Excuse me. Is possible to hear me?
Yes.
Okay, thank you so much. I will start to share the presentation, the screen. And I would like to know, please, if it is possible to see the screen. Thank you so much.
We can see.
Okay, so we will start. Hello, ICREPQ Congress 2025. My name is Alan Calderon, representing to Pontificia Universidad Católica del Perú and in the master program mechatronic, as well as for the Technische Universität Ilmenau in Deutschland, in the nanostructures of science physics group. This research prepared with Professor Benjamin Barriga, Julio Tafur, and the colleague Ricardo Alvarez. We are presenting for you the smart devices based on nanostructures according to adapt turbojets to work with renewable energy. The problematic that we are dealing, it is given because of Peru nowadays has the task to enhance turbojets that work for small airplanes. In this context, it is necessary to analyze how to enhance the power of older turbojets. While this problematic, we found and proposed the following solutions. Because of most of application needs green energy according to care environment conditions. By other side, to care also the power of these turbojets, which will be connected with small airplanes that can be used for the army force in Peru. And the proposed solution based on the target, how could be possible to integrate nanostructures to enhance this performance of turbojets. Moreover, how it also could help to use new kind of green energy in the fuel of these turbojets. Given these proposed solutions, we needed to analyze the problematic by mathematical modeling, as well as equation 1 and equation 2 are representing by modulating functions the dynamic by translation and rotational effects of the machinery that will include turboreactors or turbojets. Moreover, equations 3 and 4 looks for the thermodynamic effects, independence of enthalpy and the interchanging temperature in the entrance and exit of the fuel consumed. As well as equation 5 and 6 are the solutions based on modulating functions owing to achieve the coefficients A0, A1, A2, C0, C1, C2. Therefore, we could achieve a mathematical model to describe the effects over the turbojet as it is represented in the figure 1, consequently by 4 steps, depending on the measuring information by sensors that we propose how to elaborate this, as well as to give the information what physical variables measured by the main control system, getting action over actuators of the turboreactors, and finally to verify if the results of the fuel consumed could care or not the environment conditions. Results. We need in our project to verify that the sensors prepared for this task has enough short response time that could help to solve the intricate mathematical modeling due to achieve the performance over the system. In this situation, we designed our own sensor based on nanostructures that are shown or described in the figure number 2. We look for the effect measurements over the fuel consumed and also the thrust or the impulse over the turbojet. In this situation, we needed to corroborate the static response between the thrust of the turbojet in comparison with the fuel mass flow consumed by the turbo machinery inside. We achieved some kind of linear performance over which we designed the response over the hardware system. It means, consequently, the simulations, we designed our own algorithm to be executed by a real-time controller and verifying the dynamic response of the thrust of the turbojet in comparison with the fuel mass flow that was consumed by the turbojet, but in comparison with hydrodiesel, such as, for example, some mixing of kerosene with
Alan,
water.
please.
Yes, I can hear you.
It's time.
Yeah, okay, we just finished it, and thank you so much. Yeah, we finished it. If there is any question, please.
We have a big delay, and then we follow with the next speaker.
Okay.
Thank you very much. Thank you very much.
Thank you so much, too. Thank you.
Okay. Is in the virtual room poster number 357? Poster number 357? Or poster number 373? Poster number 373? Then Rosa Pilau? Rosa Pilau?
Hello.
Hello.
Okay,
We
let
try
me
to, sorry, Rosa, we try to connect with you, but you have only 3 minutes for your presentation, if it's possible. Okay?
No. I can't find my presentation in the script. Why?
I can't see your presentation.
I know.
No. I can't.
I don't know why.
Do you see the icon in bottom of your screen?
Yes, yes.
Arrow.
Share screen. I opened it. And
Well,
then I can't find my presentation there.
I apologize, but it's impossible to do your presentation with this problem. Okay? Thank you for your interest.
I'm sorry.
Thank you, Rosa. Sorry. Then I give a finally It's impossible. Well, we are conclude our session. Enjoy the rest of the conference.
Okay, good afternoon, everybody. Welcome to this oral session A5, where 5 interesting papers will be presented about more or less renewables, converters, and also controls. Okay, I'm Luis Sainz, from the professor of the Universitat Politécnica de Catalunya, and I will be the chairman of this session. Okay, the procedure of the session will be the same as the others. First, the authors will present their corresponding papers during more or less 10, 12 minutes. And after that, we will have the opportunity to ask and discuss about the content of the papers with them, about 3, 4 minutes. Okay, I hope that this meeting will be interesting for all of us. Okay. The first paper is the first paper is a paper about generalized predictive control current for grid-connected converters with LCL filters. Okay. Close to the microphone. Yeah. You can start as you want.
Yes. Hello, my name is Petr Šimek, and I will present a contribution. Where is the presentation? I will present the contribution.
Which is your paper?
The contribution generalized predictive current control for grid-connected converter with LCL filter. We have the current control based on generalized predictive current control for the power electronic converter connected via LCL filter was developed. A design process of the control structure and its parameter will be presented, and also the current responses in simulation and analysis of the control will be presented. We can see here the basic scheme, basic diagram. Here is DC source or load. Here is the converter on the one side, and on the other side is the AC grid, and the tie between converter and grid is via LCL filter. Here are inductors and capacitors. The inductors has also parasitic resistance, and the capacitor has damping resistance. It is unlike inductors where it is parasitic parameter. Here is the resistor for damping some oscillation. The control consists of the control beginning by current and voltage measure. Here is the general predictive current controller, and its output is required voltage of the converter. The construction model in Laplace domain consists of two parts. One part considering zero grade voltage and depend only on the converter voltage. And the second part consists, the second part depends on the gate voltage and considering considering zero converter voltage and depend only on the gate voltage, and the sum of the sum or the superposition of these two parts is the gate current. For to find the algorithm, it is necessary to convert this expression to Laplace domain. There was used the Euler backward transformation, which replaced the Laplace operator by this expression, and we obtain this equation in Z domain, and it is a transfer function of the circuit in Z domain, and the EL2 is required gate voltage, required gate current, where gate is the actually gate voltage, and we wanted what must be converter voltage for the demanded voltage. For this purpose, we use a writing function. Here is I present here only very simplified principle. We have published detailed process of design and select parameter in ICREPQ Journal of Emerging and Selected Topic in Power Electronics. The principle of the design is that there is an objective function which consists of comparison or subtract the required current and the prediction in next several steps, and predicted current of the converter in the same step. And second part is sum of regulator output weighted by coefficient lambda. We use the prediction horizon 5-step, and this horizon only 1 step. The coefficient lambda and coefficient C2 there is hidden in the prediction of response to the system must be found to optimize parameter of the current of the controller responses. Here are considered parameter of the power circuit. The inductance on the converter side we have 5 millihenry and parasitic resistance 1 ohm. On the converter side we have 2 millihenry and 1/2 ohm, and capacitance 20 microfarad and damping resistor 10 ohm. The switching frequency we have 3 kilohertz and control frequency 6 kilohertz. There is 2 sampling interval to 1 switching period. We have 2 variables. There is 3D graphs, the dependency, the regulation overshoot, time of the settling time, and the bandwidth frequency of the controller for combination of the parameter C2 and lambda, and selected combination is marked by a little red square. We select parameters C2 minus 2.7 and lambda 0.3. Since there is model predictive control, it is potential problem with change of circuit parameter. Thus we have proceed some analysis what happened if the parameters change. Here is an example of change of L1 and R1. It is inductance on the converter side, and you can see if there is change by 25%, there are some changes, maybe worst or best, depending on the sign of the change. Yeah, here is example of time responses. We can see here in first instant change of voltage. We can see there is here a little peak, and here is change of reference current. And second picture, here is response to change of parameters and change of current reference. And here is yes, this is the sampled scope, and here is considered also the switching of the transistors, and harmonic analysis of the current. We can see all harmonic are under 1.3%. Yes, and as conclusion, we have developed the general predictive power control for the voltage source converter connected to grid via LCL filter. We proceed an analysis and simulation. The predictive horizon, weight coefficient lambda, and polynomial which is the main parameter of this controller are designed and examined. The current responses on the different grid files and current reference changes were presented and evaluated. And although there is the is a relatively complicated design of this controller, the controller in fact is the controller is very simple and is very robust. This which is important benefit of this control technique. Thank you for attention.
Okay. Thank you for your presentation. Is there any questions in the audience? No questions? Okay, I have one question. Nowadays there is stability concerns due to interaction between controls of converters and traditional grid components. And I'm wondering if you have analyzed these stability problems due to your control, the control that you proposed.
For this type or for this particular controller, we don't make the stability analysis, but we have designed several years ago the general predictive current controller for L filter only L filter, and we also analyze the stability. Maybe it is future task to analyze stability.
The results will be. The results were there is interaction and there is problems with the stability in your analysis.
I don't know. It is.
No, if you found any stability problems when you analyze this control with the interaction of this control with the grid.
We declare some interval of lambda and the coefficients where is the regulator, the controller stable. I don't remember if there is issues with interaction with power. Did you mean interaction with power with the grid stability?
Okay, don't worry. It's fine, it's fine. Thank you for your presentation. Okay. Next paper. The next paper is the adaptive pi-state control of two-mass oscillatory system.
Okay, so thank you very much for the introduction and welcome to my presentation about our latest research findings, in which we have previously developed a controller based on analytical setting formulas for the active damping of torsional vibrations in very long drive shafts. For that, we have now also established an adaptive tracking algorithm, which is able to correctly identify and detect load input functions which are acting on the system. So for the system itself, we are looking at deep drilling rigs or deep drilling technology. And the reason behind that is that in drilling rigs, for example, for the exploration of oil and gas fields or geothermal energy, we have lengths of up to 8 kilometers, and therefore those systems are prone for different mechanical vibrations. So the mechanical vibrations that occur are listed here on the right-hand side. We have lateral vibrations of a drill string, we have axial vibrations of the drill string, and also torsional vibrations. And especially the stick-slip effect, which is in fact a torsional vibration, significantly influences the torque which is available at the drill bit. Another problem is that this nonlinear friction effect leads to a damping removal inside of the system and therefore to increase their vibrations, which are difficult to control because of the nonlinear effect. Of course, there exist several methods in order to calculate the controller, for example, numerical solutions. The problem here is that numerical calculations have no direct correlation between the dynamics or dampings of the system and the controller parameters itself. So it's quite difficult to understand why the controller is behaving the way it is. This was the main reason why we chose to use analytical setting formulas. We published that last year in a paper in Italy, and those formulas can be applied to any system. So in order to model the controller, we have to first model the stick-slip effect, which is done by using a static friction model, the so-called Streebeck model. And you can see here the typical shape of a Streebeck curve. So the stick-slip effect itself is a periodic effect, which means at some point the drill bit doesn't rotate at all. The motor, the top drive, applies even more torque, and in the next split second, the drill bit starts to significantly rotate faster than it should be. So here, if we have no rotation of a drill bit, then we have the static friction torque acting on the system. And what's interesting here is that with an increasing rotational speed of the drill bit, the friction torque significantly decreases, which models the stick-slip effect. Before I continue on this point, I would like to briefly introduce you to our previous work. So the controller itself is modeled in the state space. We have here the general state space representation, and we have those 4 state variables. So the motor speed, omega 1, the load speed, omega 2, the shaft torque between the 2 masses, it's a 2-oscillator system, and the electric moment or torque or the air gap torque, which is provided by the motor. For this control system, we have to do a feedback, so we have to close the loop. We do that for omega 1, as presented here. We can do that for omega 2, the load speed, and both of the acting torques. So right now we have the state controller. We went a little bit further and also added a 5th state variable, which is indicated by XPI. So we have a superimposed PI controller in order to avoid permanent control deviations. You can see that here. Of course, we have to also close this loop with the motor speed. And so right now we have the PI state controller. The load side, on the other hand, is simulated or modeled by different Strebeck curves, which I have shown on the slide before. And what's interesting here is that both the PI controller and the state controller have been calculated analytically in advance on the basis of our published paper last year. So, we now have to think of some way on how to measure and model the Strebeck curves and the friction. This is the setup we have built at our institute. It's a scaled down drilling rig with a top drive servo motor on top. This one produces the driving torque for the whole system, and the about 5 meter long drill pipe transfers this driving torque to the bottom assembly, this one here. It's described a little bit more in detail on the left-hand side. So you can see here the sample holder and the rock samples which are mounted on top. You can also see that the rock samples have a pre-drilled hole. We did that by using a diamond-coated drill bit so that the drill bit in the actual experiments has some kind of guidance inside the rock. We have done that for 3 different rock samples. You can see the results in the following slide. So we have done that for granite, sandstone, and marble. These are the corresponding static friction parameters, which were identified based on those measured curves. It's interesting here, you can see that marble has the highest friction of all the 3 curves. This is mainly due to the fact that marble is softer, for example, than granite, so more material is removed during the cutting process. That material still remains in the lubrication, and this is the reason why that curve has a higher friction torque than the other ones. The problem right now is that the controller has to somehow figure out which rock formation is present at the drill bit at that exact moment. So we need some kind of adaptive tracking, because you can see the curves are different depending on the velocity. So we thought about that way, that we calculate the friction torque acting on the drill bit in a simplified manner, which means the friction torque is equal to the driving torque supplied by the motor minus the moment of inertia times the acceleration of a drill bit. You can do that if the friction acting on the drill bit is the only friction present in the system. And we can now compare that calculated friction torque with the previously measured Strebeck curves. If a difference between those two is within a previously defined tolerance band for the torque, then the corresponding feedback vector, as well as the PI controller, is selected, and it's held for a brief amount of time in order to avoid constant measuring here. So, what does the simulation scenario look like for the drilling process? At the time t equals 10 seconds, we are starting the top drive from 0 to 30 radians per second, which corresponds to 300 RPM. 10 seconds later, we apply the first rock layer, granite. 10 seconds later, at t equals 30 seconds, we apply the second rock layer, in that case, sandstone. And at the end of the simulation, we apply the third rock layer, marble. And those 3 are modeled on the basis of the Strebeck curves we have measured before. So, how does it look like? In blue, it's a little bit hard to see, but in blue we have the set point step change at t equals 10 seconds from 0 to 30 radians per second. and in red you can see the step response of the system. So I'd like to take a closer look at that peak here. So that's the change from granite to sandstone. And you can see here that the controller is able to dampen the vibrations in a very short amount of time. It's about 500 milliseconds, and also with a very relatively low overshoot in the system. So the overshoot is like from 30 radians per second to 33 radians per second. So that is totally fine. At the end, I would also like to show you some results of the adaptive tracking mechanism, because as I said earlier, the mechanism has to identify this formation change as granite, this as sandstone, and this one as marble. Otherwise, the system would become unstable. You can see that here on the right-hand side. It may look a little bit complicated, but it's not really that difficult. So we have the three different assigned feedback vectors over the simulation period of 50 seconds. There are two major conclusions you can take from these pictures. The first one is the mechanism is able to identify the correct time periods. So from 20 to 30 seconds, a feedback vector is assigned. From 30 to 40, the next one is assigned. And from 40 to the end, the last one is assigned. The values here in the lower left corner are the exact values of that feedback vector. We have calculated those values before because we have measured the Strebeck curves before. And you can see that here. R1 for granite is 348.7. And you can also see here R1 is 348.7. And that works for all the other rock types as well. So the adaptive tracking mechanism is able to correctly identify, on the one hand, the time period in which the rock formation changes, and also the correct rock formation. So it would be a problem if here from 20 to 30 seconds we have applied granite, and it would be a problem if the algorithm would detect it's marble. Then the system would become unstable because the feedback vector doesn't match the friction acting in the system. Okay, so thank you very much for your attention, and feel free to ask questions. Thank you.
Thank you for this nice presentation.
Thank you.
Any questions in the audience? Okay.
Thank you very much for an interesting presentation. You are using adaptive controller to adapt to different stone types.
Yes.
But as you are drilling deeper and deeper, the shaft gets longer and longer, obviously. Do you also plan to use adaptive mechanism to take care of this, or some other method?
Yes, so that's a good question. Indeed, you are absolutely right, because the deeper you drill, the more drill pipes get connected to the existing shaft. So also like the moment of inertia changes, and the damping changes, and the stiffness changes. And it is indeed an idea to also use the adaptive tracking to the mechanical parameters and not only to the friction parameters. Yes.
Okay, thank you.
Any other questions? Okay, I have just one question. You have characterized experimentally the Strebeck curve.
Yes.
But this is a complex problem, and I ask about the validation of your results.
Mm-hmm.
You have validated experimentally these results? What do you think about it?
Yes, so what we validated so far are the different Strebeck curves, because by using the identified parameters, I can calculate the friction acting in the system, and I can compare the friction which is calculated by the Strebeck curves with the measured friction, because in our setup we also measure that. In a real drilling setup, you cannot really measure that. For the controller itself, we have the simulation, and we have a second experimental setup at our institute, which is a very torsional, soft drive shaft with 2 asynchronous machines. And the next step inside that project is to apply the controller as well as the different rock formations on that test bench and compare it with the shown simulation.
Okay. Thank you very much.
Thank you.
Okay, next paper is 299, designation of renewable acceleration areas.
All right. Good afternoon, everybody. Dear colleagues, my name is Tamáso. I'm from Hungary, from the Hunren Center for Energy Research, and together with one of my colleagues, we are here to present our latest study and project. I must confess that I'm not an electrical engineer, so I will not present you good-looking and complex circuit blueprints, but instead I brought you some fancy and colorful maps. So, we will talk about the current and the upcoming regulation system in Hungary about wind energy development and how we will try to affect the ongoing processes. This map shows you the previous legislative environment in terms of the spatial regulations of new wind power or wind turbine investments. One of them was the crucial one. It was banned in 12 kilometers from inhabited areas in Hungary, that you can see in red on this map, while green color represents the areas that are free to be deployed for wind energy in Hungary. It's very interesting that we have only a few wind turbines operating in Hungary, only 300 megawatts for a country population with almost 10 million. So that's a really huge problem, and that's why we launched a project called Renewland, which aims to help the decision makers to create the new legislative environment in favor of new wind power developments. Some EU context, we have several new rules and in the European Union. One of them is the Renewable Energy Directive 3 that mandates that each of the member states have to designate so-called renewable acceleration areas, which are the areas for mostly solar PV and wind turbines, where the investments are much easier than other parts of each of the countries. So in this presentation, I will focus on wind only. However, in the project, we also deal with solar PV. Just some backgrounds about the Renewland project objectives. I will not tell you each and every aspect, but it was started not so long ago, and together with the Romanian and Bulgarian colleagues, we try to work out a methodology for designating these so-called renewable acceleration areas. All right, so our main task is to find pilot areas in Bulgaria, Romania, and Hungary where we can test our methodology. It's an ongoing process. We have some difficulties about data acquisition. However, for Hungary, we have very good quality and recent geodata that we This is why we chose Hungary to implement this methodology in a much more complex way than the other two countries. So I will show you this in detail in the next upcoming minutes. We did a very extensive literature review, also looking after the good practices all across Europe. And we defined the very important site suitability criteria. There are many of them. I will show you them a little bit later. We also collected the required geodata for each of these suitability criteria. We defined buffer zones and the suitable areas of these criteria, and also defined the suitability scores. We used multi-criteria decision-making in order to prioritize between these criteria, which one is more important than others, by analytic hierarchy process. And it was all done in a GIS, a geoinformatics system environment. So actually, we now have a 1.0 results for Hungary. All right, some of the suitability criteria that I mentioned you before, we altogether have 29 suitability criteria built up from 52 components. Some of them are technical, some of them are social, and the others are environmental factors. And I will show you some example a little bit later. We also created some scenarios in the paper we proposed to the conference proceedings. We only showed you the technical scenario, while we also have a social and an environmental one. And in each of these scenarios, all of the suitability criteria behave differently. Let's see some examples. In each little area in the country, we associated suitability scores according how favorable is that area in some aspects and how unfavorable it is in another. For example, you can see here we have a 1 to 10 scoring, where the 10 means the most suitable area and the 1 means the least suitable. And we also have the 0 scoring, which is a no-go area for new wind energy development. In some cases, we used gradual suitability, which most of them are associated with a distance from a certain geographical feature or phenomena. All right, some examples. Right here we can see by white on these maps the flood zones, here the bat habitat areas, water bodies, and the inhabited areas, which are no-go zones in this analysis. We also have areas which are also no-go zones, for example, the valuable vegetation, and the further you are from the valuable vegetation, the better in terms of suitability for wind turbines. And we also have these kind of aspects where there are no-go zones. Everything is free, let's say. But some of the areas, green on this map, are better than other areas, like here in red. For example, this one is the average wind speed at 150 meters above sea level. We prioritize these aspects, as I have mentioned, using analytic hierarchy process. It's a pairwise comparison in which a group of experts decide which criteria is more important than other. There are some maths in the background, and we have the criteria weights for each of the most important criteria. So the individual suitability score of the areas times the weight that we received from the AHP equals the final suitability score in any other, every corner for Hungary. Here is the final result map that you can see, which is very interesting that we have huge white areas, which means those are the no-go areas. While you can see in the legend that the lowest rated areas with red color and the highest rated areas, the most suitable ones with the green color, are very heterogeneous in the country. It doesn't mean that the red colors are suboptimal and they cannot be utilized for new wind power developments. It just means that it's less suitable than other ones. For example, yes, you can see here some nature conservancy areas, the largest ones. Those regular shapes are radar station buffers, while others are flood risk zones, but there are many other aspects. I will not show you each and every of them. Let's zoom in. You can see it in details. It has a 10-meter resolution for the country. And you can see that some of the already existing and operating wind turbines are located more or less in the green zones, so they are quite okay. But in some cases, the currently operating wind turbines are in no-go areas according to our analysis, which is a little bit strange. All right, on this histogram you can see each suitability score and their spatial extension. You can see the higher scores are the most prominent, and only the scores 9 and 10 covers a huge area in Hungary, which can be this renewable acceleration areas that I mentioned you before. So this is the suggestion for the decision makers, for the government, to designate these areas in these most green or the highest suitability score areas. And just a rough number that it's around 57 gigawatts of wind turbine capacity, only the most suitable areas in Hungary. So in conclusion, in comparison with the international literature, I think it's a very detailed and very complex, holistic analysis that we did. It's a gap filling in Hungary. It's, I think, the most recent one in the last 20 years or so. It utilizes very up-to-date geodata and also a very good spatial resolution. So this current study, I would say that it's on the national level, it's much more complex and higher in resolution, but not as high as an environmental impact assessment, which acts actually locally. It's somewhere between the two, to be honest. We are negotiating with the Ministry of the Energy because they are asked for our opinion to create this methodology and show them the results from which they can utilize to designate these acceleration areas. Actually, we can make a lot of scenarios, just adjusting the values that we utilize, and we can apply this methodology to, let's be honest, all other renewable energy technologies, not just wind energy. Thank you for your attention.
Okay, thank you for your presentation. Any questions about the paper? No questions? Okay, I have one question. I suppose that the weighting values that you show in slide 14 are very important or critical for the final results. And my question is, which is the criterion to fix these weighting values?
Yes, actually it's the most important part, let's say, because we can adjust these values as we wish. It's a little bit subjective. However, this process that I showed you, this AHP, aims to be very objective as much as it can. But perhaps another expert group would recommend other values in this comparison, and the whole map will change at the end. Yeah.
Okay. Thank you very much.
You're welcome.
Okay, next paper is the paper 323, dual proposed DC-DC AC PWM modular power converter. You want?
Hello everyone, my name is Carlos Roncero Clemente. I'm coming from the University of Extremadura here in Spain, and today I'm going to talk about some results that we are carrying out in a project, and I hope you enjoy. Well, the outline of the presentation will follow the next step. First of all, I will try to put into a frame, and I will try to justify the motivation of proposing this structure of this power converter. After that, I will be more focused on the main topology and also about the main feature of this power converter itself. After that, I will talk about previous application that we have already validated in simulation in order to continue with the motivation of explaining about this. And at the end, I will talk about the particular application that we are presenting in this event, the dual output hybrid converter arrangement, to finalize with some conclusion. Well, first of all, why universal or dual purpose converter? Why we are researching about this? What is the motivation? Well, at the beginning, everyone knows that the power system started to operate in a very particular way, with the power flow arranged in a unidirectional way, and with a bidirectional informational flow, okay, in a very linear way, with very well known the stock of the fuels, the protection system was more or less simple. But since 20 years ago, we started to observe at the distribution network level some distributed generation here, mainly based on green power, that changed completely the paradigm. We started to observe power flows at the distribution level itself, and also in a bidirectional way from the transmission level to the consumer level. It is well known as distributed power system, and when thinking about, okay, we have generation at the distribution level, we are not thinking about to be isolated to the main grid, to the transmission network, and academia and research started to think about AC microgrid. What is a microgrid? A microgrid is an entity that can be considered like a group of resources of generator and load that can be disconnected or in-grid connected. The architecture of an AC microgrid, it's depicted here right now, and we can observe many power converters. We have different generator, different kind of load, and as by definition, the system can be operated in grid connected or in islanded mode. Well, some challenges appear when this kind of structure become more and more popular. For example, we started to observe some harmonic problems, some imbalance because we don't have the same storage system as the classical power system with the inertia, the inherent inertia of the big synchronous machine. There will started to appear some coupling between active power and reactive power because the distribution network is more resistive than inductive, and so there are some affection between active and reactive power coupling. And the system became more unstable. Analyzing this amount of power converter and generator and load, we started again to think about why don't we use directly DC microgrid, and the discussion between AC and DC system appear again, and the architecture or the topology of the system will be like this. We will simplify some system, and this system presents some potential benefits, and the transition from AC to DC, it's becoming to be analyzed and becoming to be under a discussion. And some of the benefits of the forcing benefits are there will not be reactive power, we will have less power converter stages, we will have reduced losses, we can link and we can match different system frequencies in a common DC microgrid, and we don't have additional short circuit power. But indeed, between this transition, now we are coexisting with hybrid DC and AC microgrids or nanogrid. We have some system, some in research or in real implementation at the industry, where are two buses, AC buses and DC buses, interconnected by different power converter. So we have a large amount of power converter, different topologies, different application. And in here is our contribution. We try to, let's say, unify or standardize the large amount of power converter. So the solution that we are proposing with this main focus in order to uniform is the dual purpose DC to AC PWM modular power converter. Basically, we are demanding some common feature for this application based on renewable. The topology must be flexible and must be operated for DC to DC conversion and for DC to AC conversion as well, in single phase, in three-phase system. Also must be modular. We have to assemble, test, or set up some microgrid in a very easy way with plug-and-play system. Also, we require simplicity, of course, if possible. If it's simple, it's better. And also, we have to pay attention on the input voltage of the renewable resource and also the voltage level of the load. And we will need some back and boost functionality depending on the voltage condition of the renewable resource. We have both a requirement to operate in bidirectional way if we are interfacing with any storage system. And finally, there will be this power converter must accept different control system, different application, because we have in a AC and DC microgrid, we will have interlinking converter, PV converter, energy storage system based converter. So we will implement different controller in both, in any of these power systems. So the solution that may fulfill all those requirements is as depicted right now. It is very simple. It provides bidirectionality. It provides back and boost operation, and it can interface between the majority of the distributed energy resource and our distribution system. Let's see how this power converter itself works in a roach way. Well, first of all, it's important to notice that this power converter will perform in a unipolar way. We can back or boost, but always we cannot change the sign of the input voltage. It seems for DC to DC application something acceptable, but from DC to AC, we have to make something. Okay, that we will say later. And also, it is possible to work in back and boost mode and in a bidirectional way. So here in the application from DC to AC, we can imagine an input voltage like this, and at the output we can have a voltage reference, something like that. We will have from DC to AC conversion a sinusoidal shape. It must be unipolar. Look where is the ground point or the reference point. And we can operate those switches during the boost operation. For example, here we have this input voltage and the boost operation is activated. this switch will be always on. It will be this. It will operate in a complementary way, always off, and those switches will be operating in a complementary way, making the short circuit of the inductance to store the energy and to boost, as in a conventional boost converter. Well, for the DC to AC operation, that could be more challenging. We can operate each basic buck and boost cell like this, like in this scheme. We can generate at the output some sinusoidal waveform with the corresponding out of phase one to the other, and in the load or in the AC grid, this offset will be cancel each other. Okay. For the DC to DC, we can parallelize all of them and to connect here to the DC grid or to any load. So with this basic buck boost cell, we can operate in a DC to AC conversion and also in a DC-DC in a more simpler way. Well, some possible ways to connect this basic boost cell. We can interface our system. Just by using one cell, we can interface with one simple DC load or one simple DC grid, and also with three basic modules, or even four. We can interface with three-phase load or three-phase load with 4-wire, and also with three-phase 3-wire grid, or with 3-phase and 4-wire grids. Previously, we have already developing and tested some application working as grid following mode. Okay, here we have the paper we published last year, where we developed a control system for this structure working as grid following. Okay, we are connected to any of those grids. It is very general structure, and we have tested the same control system just by using 3-cell or 4-cell or 2-cell or just 1 cell to connect to DC or different kind of 3-phase grid. After that, we also we were also focusing the grid forming application when we are working in islanded mode, and we published at the end of last year the control system to operate the same structure, the same power converter in a modular way to interface with different load, assuring the voltage and the frequency at the point of common coupling, and it performed quite well. And the last contribution before this event, at the beginning of this year, we were focused on the operation of this interlinking converter, the basic buck boost functionality, as interlinking. So we have from one port the AC bus, and in the other port we have the DC bus. Well, another application that it's possible to do by assembling different modules is the dual output hybrid converter arrangement. What is the dual output? It is a multi-port converter, where we will supply simultaneously DC load and AC load with the same structure, with the same power converter, and we will see how we are going to connect our proposal to simultaneously supply both loads. Here we can see how it is connected. 3 basic buck boost cells, 3 are connected to a 3-phase load. The neutral of this load is connected to the active point of a 4th basic buck boost cell. This neutral is connected to, for example, 350 volts, and we can connect between the negative rail of the source and the load. We have a common ground system. We are simultaneously supply a 3-phase load and also a DC load. In order to verify this, we have just tested in simulation in Plex software a modulation techniques to simultaneously supply both systems, and here we have the main result. We have tested different load changes, both in the AC, represented in the green line, it is the AC power, and here is the DC power. The main waveform shows a proper performance. It is working just in open loop. We are not focused, or we are not developed yet the closed loop system to provide more functionalities. We just wanted to validate the concept or the idea, and it seemed it could perform well to simultaneously supply the both load. For example, we can see here the unipolar waveform in the three main back-boost branches. We can see here the output voltages at in a unipolar way, and the load is supplied in with a bipolar because this offset is cancel each other. Okay. So the future activities or the challenge we are now dealing with are the following. First of all is to experimentally validate all the previous control system and application that has been published in the last month. We have already assembled, designed and assembled let's say, the prototype. Also, we are exploring in parallel the integration of artificial intelligence inspired control system in order to integrate this power converter into operating with a big data environment, with many prosumers, with many kind of load, with forecast prediction as well. And also we are starting to analyze how to implement into the control system virtual inertia approaches, considering in the DC side of the microgrid virtual capacitor, and in the AC side of the microgrid the virtual synchronous generator inertia. So it is all from my side. Hope you enjoyed, and I will be thankful if you have any question.
Okay, thank you for your presentation.
Thanks.
Any questions?
That your DC grid and your AC grid have some DC offset. So what about protection if you have an important part of DC in the AC system?
Well, you are talking about a grounding system or another, or over voltage, for example?
For example, residual current detection and simply safety for humans.
Well, I will explain. Well, you are right that, for example, in this terminal we will have 350 volt, and in those terminals we will have 350 plus 325, for example. So almost 700 volt. We are still in low voltage system, and capacitor, varistor, protection system are still under an acceptable range in my opinion. But of course, the grounding and the leakage current should be studied carefully. The testing, the preliminary idea was validated in ideal condition, no harmonic flowing, no triple order harmonic flowing in the three-phase system that can affect, but I guess it could be possible to solve with an extra module providing an active control of this, let's say, for a neutral current path. But of course, we have to pay attention about the grounding. I have seen some studies that they consider grounded this terminal, and the other is below the ground. But okay, in the worst case, we will have 700 volt, more or less, between this and ground. And I guess it could be possible to analyze and feasible to implement in a real application. But of course, it will require a special and carefully.
Indeed, if it's a problem, I see a solution. So if you double the basic boost cell D with a plus and minus output, and not between...
With a bipolar DC microgrid.
Yeah, bipolar, but and then the offset is never coming to the user.
Yeah, I think this bipolar approach, something like this, It is like the bipolar application and putting this to the neutral, to the to the ground.
Never have the minus, common minus to the user.
Yeah.
Yeah.
Thank you for your remarks. Thanks.
Thanks.
Any other question? Okay, thank you very much for your presentation.
Okay.
Next paper is paper 327, PV damping resistor.
To look at the Spanish. Yeah, thank you. So, my name is Alex van den Bossen, and the co-author is Kamran Hafiz. He mainly did the simulations where I did the practical work and the fundamental aspects of it. So, yeah. I used the abstract to highlight it a little bit, and yeah, there are a few problems today. So, we have an oversized PV peak compared to KVA in most of solar parks, but it is not used. And especially in the northern countries, this is an aspect which is important. And we have a lot of excess of power in summer in the northern countries. So the idea is, yeah, can we not put something low cost to harvest a part of that? And my idea was a kind of dump resistor, but what to use with that excess of energy. So, yeah, we could put it at the DC side of a grid-tied inverter, but it is not sure that it's stable and how will it react in practice, and that's what I experimented. So the practical use of it for the moment is to using hot water for killing weed. Here in Spain, or in Spain in general, you have no grass in the summer, but in Belgium it still rains, and this is a practical problem where a lot of chemicals are used. So I don't give the example of Flanders where I come from, because yeah, you have Belgium, which is quite heterogeneous. In the northern part you have a lot of PV, and in the southern part 3 times less per inhabitant. So in Flanders we are closer to the Netherlands. And there you see it already. Oh yeah, moment. The pointer is, yeah, there. Yeah. So the cumulative installed PV in the Netherlands is something like 24.4 gigawatt. They are not used always at the same moment because yeah, some parts are shut down, curtailment and things like these, and also they are not always always in the same direction to the sun. But the peak demand is only 19 gigawatt. So you see already the problem that even if you have no wind and no nuclear and no combined heat power and all these things, even if you don't have these things, you still have an excess of PV power compared to the peak demand at some moments of the year. So the problem is there. At least it gives the effect that it generates negative feed-in prices. Okay, at the high voltage level, it can be beyond 100 euros negative. But in last months, we had even some providers that asked also negative prices in average of the whole month. So you inject energy in the month, and the more you inject, the more you have to pay. So that's a new problem. That's what's happening last month. And yeah, so the idea is how to use that excess of power in summer. And yeah, you could do it at the local level or more general, but the problem is there. So I look at a typical inverter, grid-tied inverter, which is yeah, at the top left. So PV panel, DC-DC converter to match the maximum power point, and then a DC to AC and to the grid. Okay, that's a standard way of doing. What I propose is to see, yes, but if we could put a resistor there, what happens? So already there, the tendency in the Netherlands and more in Belgium, even for private, is to install 1.5 to 3 times more kilowatt peak than KVA inverter. In southern countries, it's not that strong, but in fact, the sun is most useful when it's cloudy. So, and when it's sun, you have a more problem with excess. So the idea is, yeah, could you put a resistor there? In fact, it changes the apparent voltage current characteristic for the inverter. And it means that at high voltage, you will have, the inverter will see a lower current. But the maximum power point change seems not to change that much. So if there is more power than the inverter can absorb, you might put that resistor, but even then, you change the characteristic. Yeah, moment. Yeah, you change the characteristic, but this is, for instance, what you get without parallel resistor. With the parallel resistor, no change when voltage is 0, okay, and it goes gradually down. Let's say that this point could be nearer to that. Yeah, you will not see it that much in the power when you do that. There is a main advantage in the whole thing, is that you never will draw electricity from the grid when you do that. So you are sure that you will not pay a lot when there is a cloud which is passing by. So questions are, how far will it be from the maximum power point? Okay, yeah. How to control it? Certainly not chopping, forbidden, because the maximum power point will, the tracker will not like these things, and you would have problems with the distributing company and so on. What would be the control algorithm? And will it be stable when you do that? We'll see. The simplest control algorithm I found was the following. So when you start with a place where you have no resistor, and you see that if the sun power rises, that the voltage at the DC level rises above the maximum power point, typically 5–10% above. So if you have 5% more than the maximum power point at the DC level input, you know the converter cannot follow. And this is a moment to turn your additional resistance on. And when you have maybe 70% of the voltage anymore, the converter still works, but yeah, you better turn it off. You have to avoid in the really low voltage zone, because the converter could remain at a very low voltage and high current. So that's a reason to turn off at that place. So basically, it's a large hysteresis control. Can be done in many ways, analog, microcontroller, Arduino. So I think about even an analog control, because it needs so low current that it can be done without any additional power supply, without any electrolytic capacitor. But it means that, that the system could last the same time as your PV panels and not be shortened by the technology of some kind of a converter. So that's basically the control scheme. So I defined the hysteresis points. Here, if you know a little bit about power electronics, you can, and control electronics, you can use maybe 2 milliamps if you do your best 1 milliamp. Why? Because maybe each quarter of an hour or something like this, you have to switch on or off of when a cloud passes or something like this. You have to switch that transistor, but at such a low frequency that you don't need a lot of charge to discharge and charge that gate of the transistor. So it can be really low power and long life by this. Yeah, this voltage divider is mainly to decide to switch on and off. Yeah, we compare also with what existed. So I didn't invent hot water, for sure. So if you look at what's existing in the Netherlands, in England mainly, they are used to kill weed with hot water. But they use, for instance, fuel to do that. And yeah, you hire such a system or a guy which operates it. Yeah. But it uses a lot of conventional fuel. If it's not fuel, it's gas, or it's not gas, it's natural gas if it's on a fixed place. But anyhow, it's fossil. On the other hand, you have a lot of chemicals which are forbidden, certainly the glyphosate, and yeah, salt, vinegar, and so on, and are not better for nature. They accepted an alternative, which is pelargonic acid, but this is even more expensive than the glyphosate. So, yeah, it's not a good alternative. Some companies started with mechanical removal, with sand, or to put sand or gravel, or very short cutting. And then, yeah, you have still the alternative on the private level, which is a hot air burner based on electricity. I tried it as well. If you have a little bit of heavy grass, you need 10 seconds before you can heat it. So it is much slower than applying hot water. And yeah, it pollutes air, mainly for the operator. And it may start fire. This might be important in countries which are quite dry. So there was also a question, if you add the resistance, will it be stable? So I experienced it, I tried it out. In fact, the maximum power point algorithms are so slow that there is no problem, in fact. But my co-author tried it out with an algorithm, the traditional algorithm. If you try a different voltage, and if the voltage, if the power is higher, it seems that you have to move to a higher voltage. If the power is lower, you have to go in the opposite side. And they do it mainly quite slowly to avoid that there are instabilities with grid or whatsoever. What I say in words is mainly what's in that decision making. Next is there you have on the left you have an original characteristic, and if you put a resistor parallel, the slope changes. So it will be lower current at higher voltage. Practically, what happens is that your peak power is less sharp. So there you see that peak power, and this top is smoother. So he tried to see what happens with the disturbance, and yeah, there you see one. And if you introduce a disturbance, what the power does, and here in this case, it's not so strange that it acts like this. So much less disturbance in this case. Why? Because if you move away, because the peak power is flatter, you don't have much effect of that. So that's what I did. I used an old boiler of 80 liter and put the resistor on the input of the photovoltaic, and you see an iron watering can, because you cannot use plastic, it's too hot, on wheelbarrow wheels, but I can assure you it's too heavy to move it when it's full. So you have to empty it on the place and then water. You can imagine other things than doing it like this, but it's quite convenient in the private level. This is not my house, it's just an atelier, so. And you could see the difference, yeah, hardly, because in the beginning it has been treated, so it's brown, and further on it's green, but difficult to see. The next one will be more clear. So this is what you can obtain as a finishing. So if you do gardening or something like this, you want to have some good effect, and that's, yeah, you see how accurate it can be, where you apply it and where it's not applied. Also, you have chives here and oregano there and flowers. You can eat the vegetables or the condiments which are growing close to you, because you simply don't use toxic products. So can you enlarge that system? True, industrial, PV farms, schools, sports centers, municipalities, and so on can have much larger systems, but they also put more kilowatt peak than kVA in the system. I got an example of, in the harbor of Ghent, some company that imports wood, and they had 1 megawatt on the roofs. So, yeah. Probably they are designing the thing with a factor 2, and that means that 500 kilowatt is possible to inject to dump, let's say, in resistive heating. If you do that, you get 10 cubic meter volume hot in 2 hours. So the idea is that the systems exist in agriculture, but for manure, if you insulate them thermally and you adapt the circuit, there are a lot of them which are not active anymore because their system is not compliant with the actual way of dispensing it. So it would not be that difficult to adapt existing systems. Conclusion. Dumping of excess of solar is an idea, but how can we do it, and which application could be? Summer-winter storage, it's quite expensive. You need a lot of volume. I have another publication on that. Hydrogen, yes, but in a limited number of hours, it would not be efficient. Maybe you could distill things if processes need that. But hot water for killing air seems affordable, renewable, and low pollution. So because we connect it at the DC side, no power is drawn from the grid, and a simple hysteresis control can do it. taking it for the grid could be also possible because in some moments of the day, the electricity price is so low that it could be possible. But then there is an imperative question that taxes should be cancelled when high voltage prices are negative. It would solve a lot of problems, but this is a political question. So I can thank you for your attention, and if there are questions, I will be glad to answer them. Mr. Chairman.
Thank you for your presentation. Yeah. Any questions?
Thank you for the presentation. It was really interesting idea, and I'm wondering if you have considered how can this system will affect the inverter operation under partial shadow condition, because you are connecting and switching one resistor in parallel that modify the curve, and I don't know if you have considered this. Thank you.
So if you switch on the resistance and you are sufficient above the normal maximum power point voltage, you remain above the maximum, you may remain even above the maximum power of the inverter. So at that moment you see nothing. But even then, it is similar to, for instance, but less severe as switching off the PV or having a sharp object passing by. Yeah, a bird that comes sitting on PV or whatsoever. In fact, PV converters should be robust with a part of the power changing. So it's not something exceptional for PV converters to do that. In fact, you will also not have one resistor in a big system. I didn't discuss that because but you could have several resistances and several hysteresis systems on the same system, so that would reduce the steps which you introduce. I'm not saying that this is the final thing of that type of technology, but I wanted to draw the attention on what the possibilities could be.
Yes, yes. Thank you very much, and congratulations for the presentation and the application.
Okay, thank you for your presentation.
Yeah.
Okay.
Thank you, Mr. Chairman.
Okay. This is the last paper in the list. I think that. Okay, so this is the last paper. Thank you for your attention and enjoy the afternoon.